Unit 6 Equilibrium. Objectives. After studying this unit, you will be able to identify dynamic nature of equilibrium involved in physical and chemical processes, state the law of equilibrium, explain characteristics of equilibria involved in physical and chemical processes, write expressions for equilibrium constants, establish a relationship between Kp and Kc, explain various factors that affect the equilibrium state of a reaction, classify substances as acids or bases according to Arrhenius, Bronsted-Lowry and Lewis concepts. Classify acids and bases as weak or strong in terms of their ionization constants. Explain the dependence of degree of ionization on concentration of the electrolyte and that of the common ion. Describe pH scale for representing hydrogen ion concentration. Explain ionization of water and its dual role as acid and base. Describe ionic product Kw and pKw for water. Appreciate use of buffer solutions. Calculate solubility product constant. Chemical equilibria are important in numerous biological and environmental processes. For example, equilibria involving O2 molecules and the protein hemoglobin play a crucial role in the transport and delivery of oxygen from our lungs to our muscles. Similar equilibria involving CO molecules and hemoglobin account for the toxicity of CO. When a liquid evaporates in a closed container, molecules with relatively higher kinetic energy escape the liquid surface into the vapor phase, and number of liquid molecules from the vapor phase strike the liquid surface and are retained in the liquid phase. It gives rise to a constant vapor pressure because of an equilibrium in which the number of molecules leaving the liquid equals the number returning to liquid from the vapor. We say that the system has reached equilibrium state at this stage. However, this is not static equilibrium, and there is a lot of activity at the boundary between the liquid and the vapor. Thus, at equilibrium, the rate of evaporation is equal to the rate of condensation. It may be represented by H2O liquid to and fro, H2O vapor. The double half arrows indicate that the processes in both the directions are going on simultaneously. The mixture of reactants and products in the equilibrium state is called an equilibrium mixture. Equilibrium can be established for both physical processes and chemical reactions. The reaction may be fast or slow depending on the experimental conditions and the nature of the reactants. When the reactants in a closed vessel at a particular temperature react to give products, the concentrations of the reactants keep on decreasing, while those of products keep on increasing for some time, after which there is no change in the concentrations of either the reactants or products. This stage of the system is the dynamic equilibrium, and the rates of the forward and reverse reactions become equal. It is due to this dynamic equilibrium stage that there is no change in the concentrations of various species in the reaction mixture. Based on the extent to which the reactions proceed to reach the state of chemical equilibrium, these may be classified into three groups. 1. The reactions that proceed nearly to completion and only negligible concentrations of the reactants are left. In some cases, it may not be even possible to detect these experimentally. 2. The reactions in which only small amounts of products are formed and most of the reactants remain unchanged at equilibrium stage. 3. The reactions in which concentrations of the reactants and products are comparable when the system is in equilibrium. The extent of a reaction in equilibrium varies with the experimental conditions such as concentrations of reactants, temperature, etc. Optimization of the operational conditions is very important in industry and laboratory so that equilibrium is favorable in the direction of the desired product. Some important aspects of equilibrium involving physical and chemical processes are dealt in this unit, along with the equilibrium involving ions in aqueous solutions, which is called as ionic equilibrium. 6.1 Equilibrium in physical processes. The characteristics of system at equilibrium are better understood if we examine some physical processes. The most familiar examples are phase transformation processes, example, solid to liquid and back, liquid to gas and back, solid to gas and back. 6.1.1 Solid-liquid equilibrium. Ice and water kept in a perfectly insulated thermos flask, no exchange of heat between its contents and the surroundings, at 273 K, and the atmospheric pressure are in equilibrium state, and the system shows interesting characteristic features. We observe that the mass of ice and water do not change with time and the temperature remains constant. However, the equilibrium is not static. The intense activity can be noticed at the boundary between ice and water. Molecules from the liquid water collide against ice and adhere to it, and some molecules of ice escape into liquid phase. There is no change of mass of ice and water, as the rates of transfer of molecules from ice into water and of reverse transfer from water into ice are equal at atmospheric pressure and 273 K. It is obvious that ice and water are in equilibrium only at particular temperature and pressure. For any pure substance at atmospheric pressure, the temperature at which the solid and liquid phases are at equilibrium is called the normal melting point or normal freezing point of the substance. The system here is in dynamic equilibrium, and we can infer the following. 1. Both the opposing processes occur simultaneously. 2. Both the processes occur at the same rate so that the amount of ice and water remains constant. 6.1.2 Liquid-vapour equilibrium. This equilibrium can be better understood if we consider the example of a transparent box carrying a U-tube with mercury, manometer. Drying agent like anhydrous calcium chloride or phosphorus pentaoxide is placed for a few hours in the box. After removing the drying agent by tilting the box on one side, a watch glass or petri dish containing water is quickly placed inside the box. It will be observed that the mercury level in the right limb of the manometer slowly increases and finally attains a constant value. That is, the pressure inside the box increases and reaches a constant value. Also, the volume of water in the watch glass decreases. Figure 6.1. Initially, there was no water vapor or very less inside the box. As water evaporated, the pressure in the box increases due to addition of water molecules into the gaseous phase inside the box. The rate of evaporation is constant. However, the rate of increase in pressure decreases with time due to condensation of vapor into water. Finally, it leads to an equilibrium condition where there is no net evaporation. This implies that the number of water molecules from the gaseous state into the liquid state also increases till the equilibrium is attained. That is, rate of evaporation equals rate of condensation. H2O liquid, 2 H2O vapor and reverse. At equilibrium, the pressure exerted by the water molecules at a given temperature remains constant and is called the equilibrium vapor pressure of water or just vapor pressure of water. Vapor pressure of water increases with temperature. If the above experiment is repeated with methyl alcohol, acetone, and ether, it is observed that different liquids have different equilibrium vapor pressures at the same temperature, and the liquid which has a higher vapor pressure is more volatile and has a lower boiling point. If we expose 3 watch glasses containing separately 1 milliliter each of acetone, ethyl alcohol and water to atmosphere and repeat the experiment with different volumes of the liquids in a warmer room, it is observed that in all such cases, the liquid eventually disappears and the time taken for complete evaporation depends on 1. The nature of the liquid, 2. The amount of the liquid, and 3. The temperature. When the watch glass is opened to the atmosphere, the rate of evaporation remains constant, but the molecules are dispersed into large volume of the room. As a consequence, the rate of condensation from vapor to liquid state is much less than the rate of evaporation. These are open systems and it is not possible to reach equilibrium in an open system. Water and water vapor are in equilibrium position at atmospheric pressure 1.013 bar and at 100 degrees Celsius in a closed vessel. The boiling point of water is 100 degrees Celsius at 1.013 bar pressure. For any pure liquid at 1 atmospheric pressure, 1.013 bar, the temperature at which the liquid and vapors are at equilibrium is called normal boiling point of the liquid. Boiling point of the liquid depends on the atmospheric pressure. It depends on the altitude of the place. At high altitude, the boiling point decreases. 6.1.3 Solid-vapour equilibrium. Let us now consider the systems where solids sublime to vapor phase. If we place solid iodine in a closed vessel, after some time the vessel gets filled up with violet vapor and the intensity of color increases with time. After a certain time, the intensity of color becomes constant and at this stage equilibrium is attained. Hence, solid iodine sublimes to give iodine vapor and the iodine vapor condenses to give solid iodine. The equilibrium can be represented as I2 solid to I2 vapor and reverse. Other examples showing this kind of equilibrium are camphor solid to camphor vapor and reverse, NH4Cl solid to NH4Cl vapor and reverse. 6.1.4 Equilibrium involving dissolution of solid or gases in liquids. Solids in liquids. We know from our experience that we can dissolve only a limited amount of salt or sugar in a given amount of water at room temperature. If we make a thick sugar syrup solution by dissolving sugar at a higher temperature, sugar crystals separate out if we cool the syrup to the room temperature. We call it a saturated solution when no more of solute can be dissolved in it at a given temperature. The concentration of the solute in a saturated solution depends upon the temperature. In a saturated solution, a dynamic equilibrium exists between the solute molecules in the solid state and in the solution. Sugar solution gives sugar solid and reverse. And the rate of dissolution of sugar equals rate of crystallization of sugar. Equality of the two rates and dynamic nature of equilibrium has been confirmed with the help of radioactive sugar. If we drop some radioactive sugar into saturated solution of non-radioactive sugar, Then, after some time, radioactivity is observed both in the solution and in the solid sugar. Initially, there were no radioactive sugar molecules in the solution, but due to dynamic nature of equilibrium, there is exchange between the radioactive and non-radioactive sugar molecules between the two phases. The ratio of the radioactive to non-radioactive molecules in the solution increases till it attains a constant value. Gases in liquids. When a soda water bottle is opened, some of the carbon dioxide gas dissolved in it fizzes out rapidly. The phenomenon arises due to difference in solubility of carbon dioxide at different pressures. There is equilibrium between the molecules in the gaseous state and the molecules dissolved in the liquid under pressure, that is, CO2 gas to CO2 in solution and reverse. This equilibrium is governed by Henry's law, which states that the mass of a gas dissolved in a given mass of a solvent at any temperature is proportional to the pressure of the gas above the solvent. This amount decreases with increase of temperature. The soda water bottle is sealed under pressure of gas when its solubility in water is high. As soon as the bottle is opened, some of the dissolved carbon dioxide gas escapes to reach a new equilibrium condition required for the lower pressure, namely, its partial pressure in the atmosphere. This is how the soda water in bottle, when left open to the air for some time, turns flat. It can be generalized that 1. For solid to liquid equilibrium and reverse, there is only one temperature melting point at 1 atm 1.013 bar at which the two phases can coexist. If there is no exchange of heat with the surroundings, the mass of the two phases remains constant. 2. For liquid to vapor equilibrium and reverse, the vapor pressure is constant at a given temperature. 3. For dissolution of solids in liquids, the solubility is constant at a given temperature. 4. For dissolution of gases in liquids, the concentration of a gas in liquid is proportional to the pressure concentration of the gas over the liquid. These observations are summarized in Table 6.1. Table 6.1. Some features of physical equilibrium. Process: liquid to vapor and reverse. Example: H2O liquid to H2O gas and reverse. Conclusion: pH2O constant at given temperature. Process: solid to liquid and reverse. Example: H2O solid to H2O liquid and reverse. Conclusion: melting point is fixed at constant pressure. Process: solute solid to solute solution and reverse. Example: sugar solid to sugar solution and reverse. Concentration of solute in solution is constant at a given temperature. Process: gas to gas aqueous and reverse. Example: CO2 gas to CO2 aqueous and reverse. Conclusion: gas aqueous to gas is constant at a given temperature. CO2 aqueous to CO2 gas is constant at a given temperature. 6.1.5 General characteristics of equilibria involving physical processes. For the physical processes discussed above, following characteristics are common to the system at equilibrium. 1. Equilibrium is possible only in a closed system at a given temperature. 2. Both the opposing processes occur at the same rate and there is a dynamic but stable condition. 3. All measurable properties of the system remain constant. 4. When equilibrium is attained for a physical process, it is characterized by constant value of one of its parameters at a given temperature. Table 6.1 lists such quantities. 5. The magnitude of such quantities at any stage indicates the extent to which the physical process has proceeded before reaching equilibrium. 6.2. Equilibrium in chemical processes, dynamic equilibrium. Analogous to the physical systems, chemical reactions also attain a state of equilibrium. These reactions can occur both in forward and backward reactions. When the rates of the forward and reverse reactions become equal, the concentrations of the reactants and the products remain constant. This is the stage of chemical equilibrium. This equilibrium is dynamic in nature as it consists of a forward reaction in which the reactants give products and reverse reaction in which products gives the original reactants. For a better comprehension, let's consider a general case of a reversible reaction. A plus B gives C plus D and reverse. With passage of time, there is accumulation of the products C and D and depletion of the reactants A and B. Figure 6.2. This leads to a decrease in the rate of forward reaction and an increase in the rate of the reverse reaction. Eventually, the two reactions occur at the same rate and the system reaches a state of equilibrium. Similarly, the reaction can reach the state of equilibrium even if we start with only C and D, that is, no A and B being present initially, as the equilibrium can be reached from either direction. The dynamic nature of chemical equilibrium can be demonstrated in the synthesis of ammonia by Haber's process. In a series of experiments, Haber started with known amounts of dinitrogen and dihydrogen maintained at high temperature and pressure, and at regular intervals determined the amount of ammonia present. He was successful in determining also the concentration of unreacted dihydrogen and dinitrogen. Figure 6.4, page 174 shows that after a certain time, the composition of the mixture remains the same even though some of the reactants are still present. This constancy in composition indicates that the reaction has reached equilibrium. In order to understand the dynamic nature of the reaction, synthesis of ammonia is carried out with exactly the same starting conditions of partial pressure and temperature, but using D2, deuterium, in place of H2. The reaction mixtures starting either with H2 or D2 reach equilibrium with the same composition, except that D2 and ND3 are present instead of H2 and NH3. After equilibrium is attained, these two mixtures H2, N2, NH3 and D2, N2, ND3 are mixed together and left for a while. Later, when this mixture is analyzed, it is found that the concentration of ammonia is just the same as before. However, when this mixture is analyzed by a mass spectrometer, it is found that ammonia and all deuterium containing forms of ammonia, NH3, NH2D, NHD2 and ND3, and dihydrogen, and its deuterated forms H2, HD and D2 are present. Thus, one can conclude that scrambling of H and D atoms in the molecules must result from a continuation of the forward and reverse reactions in the mixture. If the reaction had simply stopped when they reached equilibrium, then there would have been no mixing of isotopes in this way. Use of isotope deuterium in the formation of ammonia clearly indicates that chemical reactions reach a state of dynamic equilibrium in which the rates of forward and reverse reactions are equal and there is no net change in composition. Equilibrium can be attained from both sides, whether we start reaction by taking H2 gas and N2 gas and get NH3 gas, or by taking NH3 gas and decomposing it into N2 gas and H2 gas. N2 gas plus 3H2 gas gives 2NH3 gas and reverse. 2NH3 gas gives N2 gas plus 3H2 gas and reverse. Similarly, let us consider the reaction H2 gas plus I2 gas gives 2HI gas and reverse. If we start with equal initial concentration of H2 and I2, the reaction proceeds in the forward direction and the concentration of H2 and I2 decreases while that of HI increases until all of these become constant at equilibrium, figure 6.5. We can also start with HI alone and make the reaction to proceed in the reverse direction. The concentration of HI will decrease and concentration of H2 and I2 will increase until they all become constant when equilibrium is reached, figure 6.5. If total number of H and I atoms are same in a given volume, the same equilibrium mixture is obtained whether we start it from pure reactants or pure product. 6.3 Law of chemical equilibrium and equilibrium constant. A mixture of reactants and products in the equilibrium state is called an equilibrium mixture. In this section, we shall address a number of important questions about the composition of equilibrium mixtures. What is the relationship between the concentrations of reactants and products in an equilibrium mixture? How can we determine equilibrium concentrations from initial concentrations? What factors can be exploited to alter the composition of an equilibrium mixture? The last question in particular is important when choosing conditions for synthesis of industrial chemicals such as H2, NH3, CaO, etc. To answer these questions, let's consider a general reversible reaction A plus B gives C plus D and reverse, where A and B are the reactants, C and D are the products in the balanced chemical equation. On the basis of experimental studies of many reversible reactions, the Norwegian chemist Cato Maximilian Guldberg and Peter Wage proposed in 1864 that the concentrations in an equilibrium mixture are related by the following equilibrium equation. Kc equals C into D divided by A into B, equation 6.1, where Kc is the equilibrium constant and the expression on the right side is called the equilibrium constant expression. The equilibrium equation is also known as the law of mass action because in the early days of chemistry, concentration was called active mass. In order to appreciate their work better, let us consider the reaction between gaseous H2 and I2 carried out in a sealed vessel at 731 K. H2 gas 1 mole plus I2 gas 1 mole gives 2 HI gas 2 moles and reverse. 6 sets of experiments with varying initial conditions were performed, starting with only gaseous H2 and I2 in a sealed reaction vessel in first 4 experiments 1, 2, 3 and 4, and only HI in other 2 experiments 5 and 6. Experiment 1, 2, 3 and 4 were performed taking different concentrations of H2 and or I2 And with time, it was observed that intensity of the purple color remained constant and equilibrium was attained. Similarly, for experiments 5 and 6, the equilibrium was attained from the opposite direction. Data obtained from all 6 sets of experiments are given in Table 6.2. It is evident from the experiments 1, 2, 3 and 4 that number of moles of dihydrogen reacted equals number of moles of iodine reacted equals half into number of moles of HI formed. Also, experiments 5 and 6 indicate that H2 gas EQ equals I2 gas EQ. Knowing the above facts, in order to establish a relationship between concentrations of the reactants and products, several combinations can be tried. Let us consider the simple expression HI gas EQ divided by H2 gas EQ into I2 gas EQ. It can be seen from Table 6.3 that if we put the equilibrium concentrations of the reactants and products, the above expression is far from constant. HI EQ squared gas divided by H2 EQ gas into I2 EQ gas, we find that this expression gives constant value as shown in Table 6.3 in all the 6 cases. It can be seen that in this expression, the power of concentration for reactants and products are actually the stoichiometric coefficients in the equation for the chemical reaction. Thus, for the equation H2 gas plus I2 gas giving 2HI gas and reverse, following equation 6.1, the equilibrium constant Kc is written as Kc equals HI EQ squared gas divided by H2 EQ gas into I2 EQ gas, equation 6.2. Generally, the subscript EQ used for equilibrium is omitted from the concentration terms. It is taken for granted that the concentrations in the expression for Kc are equilibrium values. We therefore write Kc equals HI gas squared divided by H2 gas into I2 gas, equation 6.3. The subscript C indicates that Kc is expressed in concentrations of moles per liter. At a given temperature, the product of concentrations of the reaction products raised to the respective stoichiometric coefficients in the balanced chemical equation divided by the product of the concentrations of the reactants raised to their individual stoichiometric coefficients has a constant value. This is known as the equilibrium law or law of chemical equilibrium. The equilibrium constant for a general reaction, small a into capital A plus small b into capital B, giving small c into capital C plus small d into capital D and reverse, is expressed as Kc equals capital C raised to small c into capital D raised to small d divided by capital A raised to small a into capital B raised to small b, equation 6.4, where capital A, capital B, capital C, capital D are the equilibrium concentrations of the reactants and products. Equilibrium constant for the reaction 4NH3 gas plus 5O2 gas giving 4NO gas plus 6H2O gas is written as Kc equals NO raised to 4, H2O raised to 6 divided by NH3 raised to 4, O2 raised to 5. Molar concentration of different species is indicated by enclosing these in square bracket, and as mentioned above, it is implied that these are equilibrium concentrations. While writing expression for equilibrium constant, symbol for phases SLG are generally ignored. Let us write equilibrium constant for the reaction H2 gas plus I2 gas giving 2HI gas and reverse, equation 6.5 as Kc equals Hi raised to 2 divided by H2 into I2 equals X, equation 6.6. The equilibrium constant for the reverse reaction 2HI gas giving H2 gas plus I2 gas at the same temperature is Kc dash equals H2 into I2 divided by Hi squared equals 1 by X equals 1 divided by Kc, equation 6.7. Thus, Kc dash equals 1 divided by Kc, equation 6.8. Equilibrium constant for the reverse reaction is the inverse of the equilibrium constant for the reaction in the forward direction. If we change the stoichiometric coefficients in a chemical equation by multiplying throughout by a factor, then we must make sure that the expression for equilibrium constant also reflects that change. For example, if the reaction 6.5 is written as half H2 gas plus half I2 gas gives Hi gas, equation 6.9, the equilibrium constant for the above reaction is given by Kc dash equals Hi divided by H2 raised to half into I2 raised to half equals Hi squared divided by H2 into I2 raised to half equals X raised to half equals Kc raised to half, equation 6.10. On multiplying the equation 6.5 by N, we get NH2 gas plus Ni2 gas into D, giving 2NHI gas, equation 6.11. Therefore, equilibrium constant for the reaction is equal to Kc raised to N. These findings are summarized in table 6.4. It should be noted that because the equilibrium constants Kc and K'(C) have different numerical values, it is important to specify the form of the balanced chemical equation when quoting the value of an equilibrium constant. Problem 6.1. The following concentrations were obtained for the formation of NH3 from N2 and H2 at equilibrium at 500 K. N2 equals 1.5 into 10 raised to minus 2 m. H2 equals 3 into 10 raised to minus 2 m. And NH3 equals 1.2 into 10 raised to minus 2 m. Calculate equilibrium constant. Solution. The equilibrium constant for the reaction N2 gas plus 3H2 gas giving 2NH3 gas can be written as Kc equals NH3 raised to 2 divided by N2 into H2 raised to 3 equals 1.2 into 10 raised to minus 2 raised to 2 divided by 1.5 into 10 raised to minus 2 into 3 into 10 raised to minus 2 raised to 3 equals 0.355 into 10 raised to 3 equals 3.55 into 10 squared. Problem 6.2. At equilibrium, the concentrations of N2 equals 3 into 10 raised to minus 3 m, O2 equals 4.2 into 10 raised to minus 3 m, and NO equals 2.8 into 10 raised to minus 3 m in a sealed vessel at 800 K. What will be Kc for the reaction? N2 gas plus O2 gas gives 2NO gas. Solution. For the reaction, equilibrium constant Kc can be written as Kc equals NO squared divided by N2 into O2 equals 2.8 into 10 raised to minus 3 m squared divided by 3 into 10 raised to minus 3 m into 4.2 into 10 raised to minus 3 m equals 0.622. 6.4. Homogeneous Equilibria. In a homogeneous system, all the reactants and products are in the same phase. For example, in the gaseous reaction, N2 gas plus 3H2 gas giving 2NH3 gas, reactants and products are in the homogeneous phase. Similarly, for the reactions CH3COO C2H5 aqueous plus H2O liquid giving CH3COOH aqueous plus C2H5OH aqueous and Fe3 plus aqueous plus SCN minus aqueous giving FeSCN2 plus aqueous, all the reactants and products are in homogeneous solution phase. We shall now consider equilibrium constant for some homogeneous reactions. 6.4.1. Equilibrium constant in gaseous systems. So far, we have expressed equilibrium constant of the reactions in terms of molar concentration of the reactants and products and used symbol Kc for it. For reactions involving gases, however, it is usually more convenient to express the equilibrium constant in terms of partial pressure. The ideal gas equation is written as P into V equals N into R into T, giving P is equal to N divided by V into R into T. Here, P is the pressure in PA, N is the number of moles of the gas, V is the volume in meter cube, and T is the temperature in Kelvin. Therefore, N divided by V is concentration expressed in mole per meter cube. If concentration C is in mole per liter or mole per dm cube and P is in bar, then P equals C into R into T. We can also write P equals R into T. Here, capital R equals 0.0831 bar liter per mole K. At constant temperature, The pressure of the gas is proportional to its concentration, that is, P proportional to gas. For reaction in equilibrium, H2 gas plus I2 gas giving 2HI gas, we can write either Kc equals Hi squared divided by H2 into I2 or Kc equals Phi squared divided by Ph2 into Pi2, equation 6.12. Further, since Phi equals Hi into R into T and Pi2 equals I2 into R into T, Ph2 equals H2 into R into T, therefore Kp equals Phi squared divided by Ph2 into Pi2 equals Hi squared into RT squared divided by H2 into RT into I2 into RT equals Hi squared divided by H2 into I2 equals Kc, equation 6.13. In this example, Kp equals Kc, that is, both equilibrium constants are equal. However, this is not always the case. For example, in reaction N2 gas plus 3H2 gas giving 2NH3 gas, Kp equals PNH3 squared divided by PN2 into PH2 cube equals NH3 gas squared into RT squared divided by N2 gas into RT into H2 gas cube into RT cube equals NH3 squared into RT raised to minus 2 divided by N2 into H2 cube equals Kc into RT raised to minus 2 or Kp equals Kc into RT raised to minus 2, equation 6.14. Similarly, for a general reaction, small a into capital A plus small b into capital B giving small c into capital C plus small d into capital D and reverse, Kp equals P capital C raised to small c into P capital D raised to small d divided by P capital A raised to small a into P capital B raised to small b equals capital C raised to small c into capital D raised to small d into RT raised to C plus D divided by capital A raised to small a into capital B raised to small b into RT raised to A plus B equals capital C raised to small c into capital D raised to small d divided by capital A raised to small a into capital B raised to small b into RT raised to C plus D minus A plus B equals capital C raised to small c, capital D raised to small d divided by capital A raised to small a, capital B raised to small b into RT raised to delta n equals Kc into RT raised to delta n, equation 6.15, where delta n equals number of moles of gaseous products minus number of moles of gaseous reactants in the balanced chemical equation. It is necessary that while calculating the value of Kp, pressure should be expressed in bar because standard state for pressure is 1 bar. We know from unit 1 that 1 Pascal Pa equals 1 Nm raised to minus 2 and 1 bar equals 10 raised to 5 pascals. Kp values for a few selected reactions at different temperatures are given in table 6.5. Problem 6.3. PCl5, PCl3 and Cl2 are at equilibrium at 500 K and having concentration 1.59 m PCl3, 1.59 m Cl2 and 1.41 m PCl5. Calculate Kc for the reaction PCl5 giving PCl3 plus Cl2 and reverse. Solution. The equilibrium constant Kc for the above reaction can be written as Kc equals PCl3 into Cl2 divided by PCl5 equals 1.59 squared divided by 1.41 equals 1.79. Problem 6.4. The value of Kc equals 4.24 at 800 K for the reaction CO gas plus H2O gas giving CO2 gas plus H2 gas. Calculate equilibrium concentrations of CO2, H2, CO and H2O at 800 K if only CO and H2O are present initially at concentrations of 0.10 m each. Solution. For the reaction CO gas plus H2O gas giving CO2 gas plus H2 gas, initial concentration CO 0.1 m, H2O 0.1 m, CO2 0, H2 0. Let X mole per liter of each of the product be formed. At equilibrium, CO 0.1 minus X moles, H2O 0.1 minus X moles, CO2 X moles, H2 X moles, where X is the amount of CO2 and H2 at equilibrium. Hence, equilibrium constant can be written as Kc equals X squared divided by 0.1 minus X squared equals 4.24. X squared equals 4.24 into 0.01 plus X squared minus 0.2x within parenthesis. X squared equals 0.0424 plus 4.24 X squared minus 0.848x. 3.24 X squared minus 0.848x plus 0.0424 equals 0. A equals 3.24, B equals minus 0.848, C equals 0.0424. For quadratic equation ax squared plus bx plus c equals 0, x is equal to minus b plus or minus root of b squared minus 4ac divided by 2a. X equals 0.848 plus or minus square root of 0.848 squared minus 4 into 3.24 into 0.0424 divided by 3.24 into 2. X equals 0.848 plus or minus 0.4118 divided by 6.48. X1 equals 0.848 minus 0.4118 divided by 6.48 equals 0.067. X2 equals 0.848 plus 0.4118 divided by 6.48 equals 0.194. The value 0.194 should be neglected because it will give concentration of the reactant which is more than initial concentration. Hence, equilibrium concentrations are CO2 equals H2 equals X equals 0.067 m. CO equals H2O equals 0.1 minus 0.067 equals 0.033 m. Problem 6.5. For the equilibrium 2NOCl gas giving 2NO gas plus Cl2 gas, the value of the equilibrium constant Kc is 3.75 into 10 raised to minus 6 at 1069 K. Calculate the Kp for the reaction at this temperature. Solution. We know that Kp equals Kc into RT raised to delta N. For the above reaction, delta N equals 2 plus 1 minus 2 equals 1. Kp equals 3.75 into 10 raised to minus 6 into 0.0831 into 1069. Kp equals 0.033. 6.5. Heterogeneous Equilibria. Equilibrium in a system having more than one phase is called heterogeneous equilibrium. The equilibrium between water vapor and liquid water in a closed container is an example of heterogeneous equilibrium. H2O liquid gives H2O gas and reverse. In this example, there is a gas phase and a liquid phase. In the same way, equilibrium between a solid and its saturated solution, CaOH2 solid plus aqueous, giving Ca2 plus aqueous plus 2OH minus aqueous, is a heterogeneous equilibrium. Heterogeneous equilibria often involve pure solids or liquids. We can simplify equilibrium expressions for the heterogeneous equilibria involving a pure liquid or a pure solid, as the molar concentration of a pure solid or liquid is constant, that is, independent of the amount present. In other words, if a substance X is involved, then Xs and Xl are constant whatever the amount of X is taken. Contrary to this, X gas and X aqueous will vary as the amount of X in a given volume varies. Let us take thermal dissociation of calcium carbonate, which is an interesting and important example of heterogeneous chemical equilibrium. CaCO3 solid gives CaO solid plus CO2 gas, equation 6.16. On the basis of the stoichiometric equation, we can write Kc equals CaO solid into CO2 gas divided by CaCO3 solid. Since CaCO3 solid and CaO solid are both constant, therefore, modified equilibrium constant for the thermal decomposition of calcium carbonate will be Kc dash equals CO2 gas, equation 6.17, or Kp equals PCO2, equation 6.18. This shows that at a particular temperature, there is a constant concentration or pressure of CO2 in equilibrium with CaO solid and CaCO3 solid. Experimentally, it has been found that at 1100 K, the pressure of CO2 in equilibrium with CaCO3 solid and CaO solid is 2 into 10 raised to 5 pascals. Therefore, equilibrium constant at 1100 K for the above reaction is Kp equals PCO2 equals 2 into 10 raised to 5 pascals divided by 10 raised to 5 pascals equals 2. Similarly, in the equilibrium between nickel, carbon monoxide and nickel carbonyl used in the purification of nickel, Ni solid plus 4CO gas gives NiCO4 gas. The equilibrium constant is written as Kc equals NiCO4 divided by CO raised to 4. It must be remembered that for the existence of heterogeneous equilibrium, pure solids or liquids must also be present, however small the amount may be at equilibrium, but their concentrations or partial pressures do not appear in the expression of the equilibrium constant. In the reaction, Ag2O solid plus 2 HNO3 aqueous gives 2 AgNO3 aqueous plus H2O liquid. Kc equals AgNO3 squared divided by HNO3 squared. Units of equilibrium constant. The value of equilibrium constant Kc can be calculated by substituting the concentration terms in moles per liter, and for Kp, partial pressure is substituted in pascals, kPa, bar or atm. This results in units of equilibrium constant based on molarity or pressure, unless the exponents of both the numerator and denominator are same. For the reactions H2 gas plus I2 gas giving 2Hi, Kc and Kp have no unit. N2O4 gas giving 2NO2 gas, Kc has unit mole per liter and Kp has unit bar. Equilibrium constants can also be expressed as dimensionless quantities if the standard state of reactants and products are specified. For a pure gas, the standard state is 1 bar. Therefore, a pressure of 4 bar in standard state can be expressed as 4 bar divided by 1 bar equals 4, which is a dimensionless number. Standard state CO for a solute of 1 molar solution and all concentrations can be measured with respect to it. The numerical value of equilibrium constant depends on the standard state chosen. Thus, in this system, both Kp and Kc are dimensionless quantities but have different numerical values due to different standard states. Problem 6.6. The value of Kp for the reaction CO2 gas plus C solid giving 2CO gas is 3 at 1000 K. If initially PCO2 equals 0.48 bar and PCO equals 0 bar and pure graphite is present, calculate the equilibrium partial pressures of CO and CO2. Solution. For the reaction, let X be the decrease in pressure of CO2, then CO2 gas plus C solid gives 2CO gas. Initial pressure CO2 gas 0.48 bar to CO gas 0. At equilibrium, CO2 gas 0.48 minus X bar to CO gas 2X bar. Kp equals PCO squared divided by PCO2. Kp equals 2x raised to 2 divided by 0.48 minus x equals 3. 4x squared equals 3 into 0.48 minus x. 4x squared equals 1.44 minus 3x. 4x squared plus 3x minus 1.44 equals 0. A is equal to 4, B is equal to 3, C equals minus 1.44. X equals minus B plus or minus root of B squared minus 4AC divided by 2A equals minus 3 plus or minus square root of 3 squared minus 4 into 4 into minus 1.44 divided by 2 into 4 equals minus 3 plus or minus 5.66 divided by 8 equals minus 3 plus 5.66 divided by 8. As value of x cannot be negative, we neglect that value. X equals 2.66 divided by 8 equals 0.33. The equilibrium partial pressures are PCO2 equals 2x equals 2 into 0.33 equals 0.66 bar. PCO2 equals 0.48 minus X equals 0.48 minus 0.33 equals 0.15 bar. 6.66 Applications of equilibrium constants. Before considering the applications of equilibrium constants, let us summarize the important features of equilibrium constants as follows. 1. Expression for equilibrium constant is applicable only when concentrations of the reactants and products have attained constant value at equilibrium state. 2. The value of equilibrium constant is independent of initial concentrations of the reactants and products. 3. Equilibrium constant is temperature dependent, having one unique value for a particular reaction represented by a balanced equation at a given temperature. 4. The equilibrium constant for the reverse reaction is equal to the inverse of the equilibrium constant for the forward reaction. 5. The equilibrium constant K for a reaction is related to the equilibrium constant of the corresponding reaction, whose equation is obtained by multiplying or dividing the equation for the original reaction by a small integer. Let us consider applications of equilibrium constant to predict the extent of a reaction on the basis of its magnitude, predict the direction of the reaction, and calculate equilibrium concentrations. 6.6.1 Predicting the extent of a reaction. The numerical value of the equilibrium constant for a reaction indicates the extent of the reaction. But it is important to note that an equilibrium constant does not give any information about the rate at which the equilibrium is reached. The magnitude of Kc or Kp is directly proportional to the concentrations of the products as these appear in the numerator of equilibrium constant expression and inversely proportional to the concentrations of the reactants. These appear in the denominator. This implies that a high value of K is suggestive of a high concentration of products and vice versa. We can make the following generalizations concerning the composition of equilibrium mixtures. If Kc greater than 10 Q, products predominate over reactants. That is, if Kc is very large, the reaction proceeds nearly to completion. Consider the following examples. A. The reaction of H2 with O2 at 500 K has a very large equilibrium constant Kc equals 2.4 into 10 raised to 47. B. H2 gas plus Cl2 gas giving 2 HCl gas at 300 K has Kc equals 4 into 10 raised to 31. C. H2 gas plus Br2 gas giving 2 HBr gas at 300 K, Kc equals 5.4 into 10 raised to 18. If Kc less than 10 raised to minus 3, reactants predominate over products. That is, if Kc is very small, the reaction proceeds rarely. Consider the following examples. A. The decomposition of H2O into H2 and O2 at 500 K has a very small equilibrium constant Kc equals 4.1 into 10 raised to minus 48. B. N2 gas plus O2 gas giving 2NO gas at 298 K has Kc equals 4.8 into 10 raised to minus 31. If Kc is in the range of 10 raised to minus 3 to 10 Q, appreciable concentrations of both reactants and products are present. Consider the following examples. A. For reaction of H2 and I2 to give Hi, Kc equals 57 at 700 K. B. Also, gas phase decomposition of N2O4 to NO2 is another reaction with a value of Kc equals 4.64 into 10 raised to minus 3 at 25 degrees Celsius, which is neither too small nor too large. Hence, equilibrium mixtures containing appreciable concentrations of both N2O4 and NO2. These generalizations are illustrated in figure 6.6. 6.6.2 Predicting the direction of the reaction. The equilibrium constant helps in predicting the direction in which a given reaction will proceed at any stage. For this purpose, we calculate the reaction quotient Q. The reaction quotient Q, Qc with molar concentrations and Qp with partial pressures, is defined in the same way as the equilibrium constant Kc, except that the concentrations in Qc are not necessarily equilibrium values. For a general reaction, small a capital A plus small b capital B giving small c capital C plus small d capital D, equation 6.19, Qc equals capital C raised to small c into capital D raised to small d divided by capital A raised to small a into capital B raised to small b, equation 6.20. Then, if Qc greater than Kc, the reaction will proceed in the direction of the reactants, reverse reaction. If Qc less than Kc, the reaction will proceed in the direction of the products, forward reaction. If Qc equals Kc, the reaction mixture is already at equilibrium. Consider the gaseous reaction of H2 with I2, H2 gas plus I2 gas giving 2HI gas, Kc equals 57 at 700 K. Suppose we have molar concentrations H2T equals 0.10 m, I2T equals 0.20 m, and HIT equals 0.40 m. The subscript T on the concentration symbols means that the concentrations were measured at some arbitrary time t, not necessarily at equilibrium. Thus, the reaction quotient Qc at this stage of the reaction is given by Qc equals HIT squared divided by H2T into I2T equals 0.40 squared divided by 0.10 into 0.20 equals 8. Now in this case, Qc8 does not equal Kc57. So the mixture of H2 gas, I2 gas and HI gas is not at equilibrium. That is, more H2 gas and I2 gas will react to form more HI gas and their concentrations will decrease till Qc equals Kc. The reaction quotient Qc is useful in predicting the direction of reaction by comparing the values of Qc and Kc. Thus, we can make the following generalizations concerning the direction of the reaction, figure 6.7. If Qc less than Kc, net reaction goes from left to right. If Qc greater than Kc, net reaction goes from right to left. If Qc equals Kc, no net reaction occurs. Problem 6.7. The value of Kc for the reaction 2A giving B plus C is 2 into 10 raised to minus 3. At a given time, the composition of reaction mixture is A equals B equals C equals 3 into 10 raised to minus 4 m. In which direction the reaction will proceed? Solution. For the reaction quotient Qc is given by Qc equals B into C divided by A squared. As A equals B equals C equals 3 into 10 raised to minus 4 m, Qc equals 3 into 10 raised to minus 4 into 3 into 10 raised to minus 4 divided by 3 into 10 raised to minus 4 squared equals 1. As QC greater than Kc, the reaction will proceed in the reverse direction. 6.6.3 Calculating equilibrium concentrations. In case of a problem in which we know the initial concentrations but do not know any of the equilibrium concentrations, the following 3 steps shall be followed. Step 1. Write the balanced equation for the reaction. Step 2. Under the balanced equation, make a table that lists for each substance involved in the reaction. A. The initial concentration. B. The change in concentration on going to equilibrium. And C. The equilibrium concentration. In constructing the table, define X as the concentration mole per liter of one of the substances that reacts on going to equilibrium. Then use the stoichiometry of the reaction to determine the concentrations of the other substances in terms of X. Step 3. Substitute the equilibrium concentrations into the equilibrium equation for the reaction and solve for X. If you are to solve a quadratic equation, choose the mathematical solution that makes chemical sense. Step 4. Calculate the equilibrium concentrations from the calculated value of X. Step 5. Check your results by substituting them into the equilibrium equation. Problem 6.8. 13.8 g of N2O4 was placed in a 1 liter reaction vessel at 400 K and allowed to attain equilibrium. N2O4 gas giving 2NO2 gas. The total pressure at equilibrium was found to be 9.15 bar. Calculate Kc, Kp and partial pressure at equilibrium. Solution. We know P into V equals N into R into T. Total volume V equals 1 liter. Molecular mass of N2O4 equals 92 grams. Number of moles equals 13.8 g divided by 92 g equals 0.15 of the gas N. Gas constant capital R equals 0.083 bar L per mole per K. Temperature capital T equals 400 K. P into V equals N into R into T. P into 1 liter equals 0.15 moles into 0.083 bar liter per mole per K into 400 K. P equals 4.98 bar. N2O4 gives 2NO2. Initial pressure N2O4 4.98 bar, 2NO2 0. At equilibrium N2O4 4.98 minus X bar, 2NO2 2X bar. Hence, P total at equilibrium equals P N2O4 plus P NO2. 9.15 equals 4.98 minus X plus 2X. 9.15 equals 4.98 plus X. X equals 9.15 minus 4.98 equals 4.17 bar. Partial pressures at equilibrium are Pn2O4 equals 4.98 minus 4.17 equals 0.81 bar. PNO2 equals 2x equals 2 into 4.17 equals 8.34 bar. Kp equals PNO2 squared divided by PN2O4 equals 8.34 squared divided by 0.81 equals 85.87. Kp equals Kc into RT raised to delta N. equals 85.87 equals Kc into 0.083 into 400 raised to 1. Kc equals 2.586 equals 2.6. Problem 6.9. 3 moles of PCl5 kept in 1 liter closed reaction vessel was allowed to attain equilibrium at 380 K. Calculate composition of the mixture at equilibrium. Kc equals 1.80. Solution. PCl5 gives PCl3 plus Cl2. Initial concentration PCl5 3, PCl3 0, Cl2 0. Let x mole per liter of PCl5 be dissociated. At equilibrium, PCl5 3 minus x, PCl3 x, Cl2 x. Kc equals PCl3 into Cl2 divided by PCl5. 1.8 equals x squared divided by 3 minus x. X squared plus 1.8x minus 5.4 equals 0. X equals minus 1.8 plus or minus square root of 1.8 squared minus 4 into minus 5.4 divided by 2. X equals minus 1.8 plus or minus square root of 3.24 plus 21.6 divided by 2. X equals minus 1.8 plus or minus 4.98 divided by 2. X equals minus 1.8 plus 4.98 divided by 2 equals 1.59. PCl5 equals 3 minus x equals 3 minus 1.59 equals 1.41 m. PCl3 equals Cl2 equals x equals 1.59 m. 6.7. Relationship between equilibrium constant K, reaction quotient Q and Gibbs energy G. The value of Kc for a reaction does not depend on the rate of the reaction. However, as you have studied in Unit 5, it is directly related to the thermodynamics of the reaction and in particular to the change in Gibbs energy delta G. If delta G is negative, then the reaction is spontaneous and proceeds in the forward direction. Delta G is positive, then reaction is considered non-spontaneous. Instead, as reverse reaction would have a negative delta G, the products of the forward reaction shall be converted to the reactants. Delta G is 0. The reaction has achieved equilibrium. At this point, there is no longer any free energy left to drive the reaction. A mathematical expression of this thermodynamic view of equilibrium can be described by the following equation. Delta G equals delta G minus plus RT ln Q, equation 6.21, where G minus is standard Gibbs energy. At equilibrium, when delta G equals 0, Q equals Kc, the equation 6.21 becomes delta G equals delta G minus plus RT ln K equals 0. Delta G minus equals minus RT ln K, equation 6.22. ln K equals minus delta G minus divided by RT. Taking antilog of both sides, we get K equals e raised to minus delta G minus divided by RT, equation 6.23. Hence, using the equation 6.23, the reaction spontaneity can be interpreted in terms of the value of delta G minus. If delta G minus less than 0, then minus delta G minus divided by RT is positive, and e raised to minus delta dg minus divided by RT greater than 1, making K greater than 1, which implies a spontaneous reaction or the reaction which proceeds in the forward direction to such an extent that the products are present predominantly. If delta G minus greater than 0, then minus delta G minus divided by RT is negative and e raised to minus delta G minus divided by RT less than 1, that is K less than 1, which implies a non-spontaneous reaction or a reaction which proceeds in the forward direction to such a small degree that only a very minute quantity of the product is formed. Problem 6.10. The value of delta G minus for the phosphorylation of glucose in glycolysis is 13.8 kilojoules per mole. Find the value of Kc at 298 K. Solution: delta G minus equals 13.8 kilojoules per mole equals 13.8 into 10 raised to 3 joules per mole. Also, delta G minus equals minus R into T into ln of Kc. Hence, ln Kc equals minus 13.8 into 10 raised to 3 joules per mole, 8.314 joules per mole per K into 298 K. ln Kc equals minus 5.569, Kc equals e raised to minus 5.569, Kc equals 3.81 into 10 raised to minus 3. Problem 6.11. Hydrolysis of sucrose gives sucrose plus H2O, giving glucose plus fructose and reverse. Equilibrium constant Kc for the reaction is 2 into 10 raised to 13 at 300 K. Calculate delta G minus at 300 K. Solution: delta G minus equals minus R into T ln Kc. Delta G minus equals minus 8.314 joules per mole per K into 300 K into ln of 2 into 10 raised to 13 equals minus 7.64 into 10 raised to 4 joules per mole. 6.8. Factors affecting equilibrium. One of the principal goals of chemical synthesis is to maximize the conversion of the reactants to products while minimizing the expenditure of energy. This implies maximum yield of products at mild temperature and pressure conditions. If it does not happen, then the experimental conditions need to be adjusted. For example, in the Haber process for the synthesis of ammonia from N2 and H2, the choice of experimental conditions is of real economic importance. Annual world production of ammonia is about 100 million tons, primarily for use as fertilizers. Equilibrium constant Kc is independent of initial concentrations, but if a system at equilibrium is subjected to a change in the concentration of one or more of the reacting substances, then the system is no longer at equilibrium and net reaction takes place in some direction until the system returns to equilibrium once again. Similarly, a change in temperature or pressure of the system may also alter the equilibrium. In order to decide what course the reaction adopts and make a qualitative prediction about the effect of a change in conditions on equilibrium, we use Le Chatelier's principle. It states that a change in any of the factors that determine the equilibrium conditions of a system will cause the system to change in such a manner so as to reduce or to counteract the effect of the change. This is applicable to all physical and chemical equilibria. We shall now be discussing factors which can influence the equilibrium. 6.8.1 Effect of concentration change. In general, when equilibrium is disturbed by the addition or removal of any reactant or products, Le Chatelier's principle predicts that the concentration stress of an added reactant or product is relieved by net reaction in the direction that consumes the added substance. The concentration stress of a removed reactant or product is relieved by net reaction in the direction that replenishes the removed substance. Or in other words, when the concentration of any of the reactants or products in a reaction at equilibrium is changed, the composition of the equilibrium mixture changes so as to minimize the effect of concentration changes. Let us take the reaction H2 gas plus I2 gas giving 2HI gas. If H2 gas is added to the reaction mixture at equilibrium, then the equilibrium of the reaction is disturbed. In order to restore it, the reaction proceeds in a direction wherein H2 is consumed. That is, more of H2 and I2 react to form HI, and finally the equilibrium shifts in right or forward direction. Figure 6.8. This is in accordance with the Le Chatelier's principle, which implies that in case of addition of a reactant or product, a new equilibrium will be set up in which the concentration of the reactant or product should be less than what it was after the addition, but more than what it was in the original mixture. The same point can be explained in terms of the reaction quotient QC. QC equals HI squared divided by H2 into I2. Addition of hydrogen at equilibrium results in QC being less than Kc. Thus, in order to attain equilibrium again, reaction moves in the forward direction. Similarly, we can say that removal of a product also boosts the forward reaction and increases the concentration of the products, and this has great commercial application in cases of reactions where the product is a gas or a volatile substance. In case of manufacture of ammonia, ammonia is liquefied and removed from the reaction mixture so that reaction keeps moving in forward direction. Similarly, in the large-scale production of CaO used as important building material from CaCO3, constant removal of CO2 from the kiln drives the reaction to completion. It should be remembered that continuous removal of a product maintains QC at a value less than Kc, and reaction continues to move in the forward direction. Effect of concentration and experiment. This can be demonstrated by the following reaction. Fe raised to 3 plus aqueous yellow plus SCN minus aqueous colorless gives FeSCN raised to 2 plus aqueous deep red. Equation 6.24. Kc equals FeSCN raised to 2 plus aqueous divided by Fe3 plus aqueous into SCN minus aqueous. Equation 6.25. A reddish color appears on adding 2 drops of 0.002 m potassium thiocyanate solution to 1 ml of 0.2 m iron 3 nitrate solution due to the formation of FeSCN raised to 2 plus. The intensity of the red color becomes constant on attaining equilibrium. This equilibrium can be shifted in either forward or reverse directions depending on our choice of adding a reactant or a product. The equilibrium can be shifted in the opposite direction by adding reagents that remove Fe3+ or SCN- ions. For example, oxalic acid H2C2O4 reacts with Fe3+ ions to form the stable complex ion FeC2O43 raised to 3-, thus decreasing the concentration of free Fe3+ aqueous. In accordance with the Le Chatelier's principle, the concentration stress of removed Fe3+ is relieved by dissociation of FeSCN raised to 2+ to replenish the Fe3+ ions. Because the concentration of FeSCN raised to 2+ decreases, the intensity of red color decreases. Addition of aqueous HgCl2 also decreases red color because Hg raised to 2+ reacts with SCN- ions to form stable complex ion HgSCN4 raised to 2-. Removal of free SCN- aqueous shifts the equilibrium in equation 6.24 from right to left to replenish SCN- ions. Addition of potassium thiocyanate, on the other hand, increases the color intensity of the solution as it shifts the equilibrium to right. 6.8.2 Effect of pressure change. A pressure change obtained by changing the volume can affect the yield of products in case of a gaseous reaction where the total number of moles of gaseous reactants and total number of moles of gaseous products are different. In applying Le Chatelier's principle to a heterogeneous equilibrium, the effect of pressure changes on solids and liquids can be ignored because the volume and concentration of a solution or liquid is nearly independent of pressure. Consider the reaction CO gas plus 3H2 gas giving CH4 gas plus H2O gas. Here, 4 mole of gaseous reactants CO plus 3H2 become 2 moles of gaseous products CH4 plus H2O. Suppose equilibrium mixture for above reaction kept in a cylinder fitted with a piston at constant temperature is compressed to 1/2 of its original volume. Then total pressure will be doubled according to P into V equals constant. The partial pressure and therefore concentration of reactants and products have changed, and the mixture is no longer at equilibrium. The direction in which the reaction goes to re-establish equilibrium can be predicted by applying the Le Chatelier's principle. Since pressure has doubled, the equilibrium now shifts in the forward direction, a direction in which the number of moles of the gas or pressure decreases. We know pressure is proportional to moles of the gas. This can also be understood by using reaction quotient QC. Let CO, H2, CH4 and H2O be the molar concentrations at equilibrium for methanation reaction. When volume of the reaction mixture is halved, the partial pressure and the concentration are doubled. We obtain the reaction quotient by replacing each equilibrium concentration by double its value. QC equals CH4 gas into H2O gas divided by CO gas into H2 gas raised to 3. As QC less than Kc, the reaction proceeds in the forward direction. In reaction C solid plus CO2 gas giving 2CO gas, when pressure is increased, the reaction goes in the reverse direction because the number of moles of gas increases in the forward direction. 6.8.3 Effect of inert gas addition. If the volume is kept constant and an inert gas such as argon is added, which does not take part in the reaction, the equilibrium remains undisturbed. It's because the addition of an inert gas at constant volume does not change the partial pressures or the molar concentrations of the substance involved in the reaction. The reaction quotient changes only if the added gas is a reactant or product involved in the reaction. 6.8.4 Effect of temperature change. Whenever an equilibrium is disturbed by a change in the concentration, pressure or volume, the composition of the equilibrium mixture changes because the reaction quotient Qc no longer equals the equilibrium constant Kc. However, when a change in temperature occurs, the value of equilibrium constant Kc is changed. In general, the temperature dependence of the equilibrium constant depends on the sign of delta H for the reaction. The equilibrium constant for an exothermic reaction, negative delta H, decreases as the temperature increases. The equilibrium constant for an endothermic reaction, positive delta H, increases as the temperature increases. Temperature changes affect the equilibrium constant and rates of reactions. Production of ammonia according to the reaction N2 gas plus 3H2 gas giving 2NH3 gas. Delta H equals minus 92.38 kilojoules per mole is an exothermic process. According to Le Chatelier's principle, raising the temperature shifts the equilibrium to left and decreases the equilibrium concentration of ammonia. In other words, low temperature is favorable for high yield of ammonia, but practically, very low temperatures slow down the reaction and thus a catalyst is used. Effect of temperature and experiment. Effect of temperature on equilibrium can be demonstrated by taking NO2 gas, brown in color, which dimerizes into N2O4 gas, colorless. 2NO2 gas gives N2O4 gas, delta H equals minus 57.2 kilojoules per mole. NO2 gas prepared by addition of Cu turns to concentrated HNO3 is collected in two 5 ml test tubes, ensuring the same intensity of color of gas in each tube, and stopper sealed with araldite. 3 250 ml beakers 1, 2 and 3 containing freezing mixture, water at room temperature and hot water 363 K respectively are taken. Figure 6.9. Both the test tubes are placed in beaker 2 for 8 to 10 minutes. After this, one is placed in beaker 1 and the other in beaker 3. The effect of temperature on direction of reaction is depicted very well in this experiment. At low temperatures in beaker 1, the forward reaction of formation of N2O4 is preferred as reaction is exothermic and thus intensity of brown color due to NO2 decreases. While in beaker 3, high temperature favors the reverse reaction of formation of NO2 and thus the brown color intensifies. Effect of temperature can also be seen in an endothermic reaction. COH2O6 raised to 3 plus aqueous, pink, plus 4Cl minus aqueous, colorless gives COCl4 raised to 2 minus aqueous, blue, plus 6H2O liquid. At room temperature, the equilibrium mixture is blue due to COCl4 raised to 2 minus. When cooled in a freezing mixture, The color of the mixture turns pink due to COH2O6 raised to 3 plus. 6.8.5 Effect of a catalyst. A catalyst increases the rate of the chemical reaction by making available a new low-energy pathway for the conversion of reactants to products. It increases the rate of forward and reverse reactions that pass through the same transition state and does not affect equilibrium. Catalyst lowers the activation energy for the forward and reverse reactions by exactly the same amount. Catalyst does not affect the equilibrium composition of a reaction mixture. It does not appear in the balanced chemical equation or in the equilibrium constant expression. Let us consider the formation of NH3 from dinitrogen and dihydrogen, which is highly exothermic reaction and proceeds with decrease in total number of moles formed as compared to the reactants. Equilibrium constant decreases with increase in temperature. At low temperature, rate decreases and it takes long time to reach equilibrium, whereas high temperatures give satisfactory rates but poor yields. German chemist Fritz Haber discovered that a catalyst consisting of iron catalyzes the reaction to occur at a satisfactory rate at temperatures where the equilibrium concentration of NH3 is reasonably favorable. Since the number of moles formed in the reaction is less than those of reactants, the yield of NH3 can be improved by increasing the pressure. Optimum conditions of temperature and pressure for the synthesis of NH3 using catalyst are around 500 degrees Celsius and 200 atm. Similarly, in manufacture of sulfuric acid by contact process, 2SO2 gas plus O2 gas gives 2SO3 gas, Kc equals 1.7 into 10 raised to 26, though the value of K is suggestive of reaction going to completion. Practically, the oxidation of SO2 to SO3 is very slow. Thus, platinum or divanadium pentaoxide V2O5 is used as catalyst to increase the rate of the reaction. Note, if a reaction has an exceedingly small K, a catalyst would be of little help. 6.9 Ionic equilibrium in solution. Under the effect of change of concentration on the direction of equilibrium, you have incidentally come across the following equilibrium which involves ions. Fe3 plus aqueous plus SCN minus aqueous gives FeSCN raised to 2 plus aqueous. There are numerous equilibria that involve ions only. In the following sections, we will study the equilibria involving ions. It is well known that the aqueous solution of sugar does not conduct electricity. However, when common salt, sodium chloride, is added to water, it conducts electricity. Also, the conductance of electricity increases with an increase in concentration of common salt. Michael Faraday classified the substances into two categories based on their ability to conduct electricity. One category of substances conduct electricity in their aqueous solutions and are called electrolytes, while the other do not, and are thus referred to as non-electrolytes. Faraday further classified electrolytes into strong and weak electrolytes. Strong electrolytes on dissolution in water are ionized almost completely, while the weak electrolytes are only partially dissociated. For example, an aqueous solution of sodium chloride is comprised entirely of sodium ions and chloride ions, while that of acetic acid mainly contains unionized acetic acid molecules and only some acetate ions and hydronium ions. This is because there is almost 100% ionization in case of sodium chloride as compared to less than 5% ionization of acetic acid, which is a weak electrolyte. It should be noted that in weak electrolytes, equilibrium is established between ions and the unionized molecules. This type of equilibrium involving ions in aqueous solution is called ionic equilibrium. Acids, bases, and salts come under the category of electrolytes and may act as either strong or weak electrolytes. 6.10 Acids, bases, and salts. Acids, bases, and salts find widespread occurrence in nature. Hydrochloric acid present in the gastric juice is secreted by the lining of our stomach in a significant amount of 1.2 to 1.5 liters per day and is essential for digestive processes. Acetic acid is known to be the main constituent of vinegar. Lemon and orange juices contain citric and ascorbic acids, and tartaric acid is found in tamarind paste. As most of the acids taste sour, the word acid has been derived from a Latin word acidus, meaning sour. Acids are known to turn blue litmus paper into red and liberate dihydrogen on reacting with some metals. Similarly, bases are known to turn red litmus paper blue, taste bitter, and feel soapy. A common example of a base is washing soda used for washing purposes. When acids and bases are mixed in the right proportion, they react with each other to give salts. Some commonly known examples of salts are sodium chloride, barium sulfate, and sodium nitrate. Sodium chloride common salt is an important component of our diet and is formed by a reaction between hydrochloric acid and sodium hydroxide. It exists in solid state as a cluster of positively charged sodium ions and negatively charged chloride ions, which are held together due to electrostatic interactions between oppositely charged species. Figure 6.10. The electrostatic forces between two charges are inversely proportional to dielectric constant of the medium. Water, a universal solvent, possesses a very high dielectric constant of 80. Thus, when sodium chloride is dissolved in water, the electrostatic interactions are reduced by a factor of 80, and this facilitates the ions to move freely in the solution. Also, they are well separated due to hydration with water molecules. Comparing the ionization of hydrochloric acid with that of acetic acid in water, we find that though both of them are polar covalent molecules, former is completely ionized into its constituent ions, while the latter is only partially ionized, less than 5%. The extent to which ionization occurs depends upon the strength of the bond and the extent of solvation of ions produced. The terms dissociation and ionization have earlier been used with different meaning. Dissociation refers to the process of separation of ions in water already existing as such in the solid state of the solute, as in sodium chloride. On the other hand, ionization corresponds to a process in which a neutral molecule splits into charged ions in the solution. Here, we shall not distinguish between the two and use the two terms interchangeably. Faraday was born near London into a family of very limited means. At the age of 14, he was an apprentice to a kind bookbinder who allowed Faraday to read the books he was binding. Through a fortunate chance, he became laboratory assistant to Davy, and during 1813-14, Faraday accompanied him to the continent. During this trip, he gained much from the experience of coming into contact with many of the leading scientists of the time. In 1825, he succeeded Davy as director of the Royal Institution Laboratories, and in 1833, he also became the first Fullerian professor of chemistry. Faraday's first important work was on analytical chemistry. After 1821, much of his work was on electricity and magnetism and different electromagnetic phenomena. His ideas have led to the establishment of modern field theory. He discovered his two laws of electrolysis in 1834. Faraday was a very modest and kind-hearted person. He declined all honors and avoided scientific controversies. He preferred to work alone and never had any assistant. He disseminated science in a variety of ways, including his Friday evening discourses, which he founded at the Royal Institution. He has been very famous for his Christmas lecture on the chemical history of a candle. He published nearly 450 scientific papers. Arrhenius was born near Uppsala, Sweden. He presented his thesis on the conductivities of electrolyte solutions to the University of Uppsala in 1884. For the next 5 years, he traveled extensively and visited a number of research centers in Europe. In 1895, he was appointed professor of physics at the newly formed University of Stockholm, serving its rector from 1897 to 1902. From 1905 until his death, he was director of physical chemistry at the Nobel Institute in Stockholm. He continued to work for many years on electrolytic solutions. In 1899, he discussed the temperature dependence of reaction rates on the basis of an equation, now usually known as Arrhenius equation. He worked in a variety of fields and made important contributions to immunochemistry, cosmology, the origin of life, and the causes of Ice Age. He was the first to discuss the greenhouse effect, calling by that name. He received Nobel Prize in Chemistry in 1903 for his theory of electrolytic dissociation and its use in the development of chemistry. 6.10.1 Arrhenius concept of acids and bases. According to Arrhenius theory, acids are substances that dissociates in water to give hydrogen ions H plus aqueous, and bases are substances that produce hydroxyl ions OH minus aqueous. The ionization of an acid HX aqueous can be represented by the following equations. HX aqueous gives H plus aqueous plus X minus aqueous, or HX aqueous plus H2O liquid gives H3O aqueous plus X minus aqueous. A bare proton H plus is very reactive and cannot exist freely in aqueous solutions. Thus, it bonds to the oxygen atom of a solvent water molecule to give trigonal pyramidal hydronium ion H3O plus H2O, see box. In this chapter, we shall use H plus aqueous and H3O aqueous interchangeably to mean the same, that is, a hydrated proton. Similarly, a base molecule like MOH ionizes in aqueous solution. According to the equation, MOH aqueous gives M plus aqueous plus OH minus aqueous. The hydroxyl ion also exists in the hydrated form in the aqueous solution. Arrhenius' concept of acid and base, however, suffers from the limitation of being applicable only to aqueous solutions and also does not account for the basicity of substances like ammonia which do not possess a hydroxyl group. Hydronium and hydroxyl ions. Hydrogen ion by itself is a bare proton with very small size, approximately 10 raised to minus 15 meters of radius, and intense electric field, binds itself with the water molecule at one of the two available lone pairs on it, giving H3O+. This species has been detected in many compounds, example H3O plus Cl minus in the solid state. In aqueous solution, the hydronium ion is further hydrated to give species like H5O2 plus, H7O3 plus, and H9O4 plus. Similarly, the hydroxyl ion is hydrated to give several ionic species like H3O2 minus, H5O3 minus, and H7O4 minus, etc. 6.10.2 The Bronsted-Lowry acids and bases. The Danish chemist Johannes Bronsted and the English chemist Thomas M. Lowry gave a more general definition of acids and bases. According to Bronsted-Lowry theory, acid is a substance that is capable of donating a hydrogen ion H+, and bases are substances capable of accepting a hydrogen ion H+. In short, acids are proton donors and bases are proton acceptors. Consider the example of dissolution of NH3 in H2O represented by the following equation. NH3 aqueous base plus H2O liquid acid gives NH4 plus aqueous conjugate acid plus OH minus aqueous conjugate base. The basic solution is formed due to the presence of hydroxyl ions. In this reaction, water molecule acts as proton donor and ammonia molecule acts as proton acceptor and are thus called Lowry-Bronsted acid and base respectively. In the reverse reaction, H plus is transferred from NH4 plus to OH minus. In this case, NH4 plus acts as a Bronsted acid while OH minus acts as a Bronsted base. The acid-base pair that differs only by one proton is called a conjugate acid-base pair. Therefore, OH minus is called the conjugate base of an acid H2O and NH4 plus is called conjugate acid of the base NH3. If Bronsted acid is a strong acid, then its conjugate base is a weak base and vice versa. It may be noted that conjugate acid has one extra proton and each conjugate base has one less proton. Consider the example of ionization of hydrochloric acid in water. HCl aqueous acts as an acid by donating a proton to H2O molecule, which acts as a base. HCl aqueous acid plus H2O liquid base gives H3O plus aqueous conjugate acid plus Cl minus aqueous conjugate base. It can be seen in the above equation that water acts as a base because it accepts the proton. The species H3O plus is produced when water accepts a proton from HCl. Therefore, Cl minus is a conjugate base of HCl and HCl is the conjugate acid of base Cl minus. Similarly, H2O is a conjugate base of an acid H3O plus and H3O plus is a conjugate acid of base H2O. It is interesting to observe the dual role of water as an acid and a base. In case of reaction with HCl, water acts as a base, while in case of ammonia, it acts as an acid by donating a proton. Problem 6.12. What will be the conjugate bases for the following Bronsted acids HF, H2SO4 and HCO3-? Solution. The conjugate bases should have one proton less in each case and therefore the corresponding conjugate bases are F-, HSO4- and CO3 2- respectively. Problem 6.13. Write the conjugate acids for the following Bronsted bases NH2-, NH3 and HCOO-. Solution. The conjugate acid should have one extra proton in each case and therefore the corresponding conjugate acids are NH3, NH4+, and HCOOH respectively. Problem 6.14. The species H2O, HCO3-, HSO4- and NH3 can act both as Bronsted acids and bases. For each case, give the corresponding conjugate acid and conjugate base. Solution. The answer is given in the following table. Species H2O, conjugate acid H3O+, conjugate base OH-. Species HCO3-, conjugate acid H2CO3, conjugate base CO3 2-. Species HSO4-, conjugate acid H2SO4, conjugate base SO4 2-. Species NH3, conjugate acid NH4+, conjugate base NH2-. 6.10.3 Lewis actions and bases. G. N. Lewis in 1923 defined an acid as a species which accepts electron pair and base which donates an electron pair. As far as bases are concerned, there is not much difference between Bronsted-Lowry and Lewis concepts, as the base provides a lone pair in both the cases. However, in Lewis concept, many acids do not have proton. A typical example is reaction of electron-deficient species BF3 with NH3. BF3 does not have a proton, but still acts as an acid and reacts with NH3 by accepting its lone pair of electrons. This reaction can be represented by BF3 plus NH3 gives BF3NH3. Electron deficient species like AlCl3, CO3 plus, Mg2 plus, etc. can act as Lewis acids, while species like H2O, NH3, OH-, etc., which can donate a pair of electrons, can act as Lewis bases. Problem 6.15. Classify the following species into Lewis acids and Lewis bases and show how these act as such. A. HO-, B. F-, C. H+, D. BCl3. Solution. A. Hydroxyl ion is a Lewis base as it can donate an electron lone pair OH-. B. fluoride ion acts as a Lewis base as it can donate any one of its 4 electron lone pairs. C. A proton is a Lewis acid as it can accept a lone pair of electrons from bases like hydroxyl ion and fluoride ion. D. BCl3 acts as a Lewis acid as it can accept a lone pair of electrons from species like ammonia or amine molecules. 6.11 Ionization of acids and bases. Arrhenius' concept of acids and bases becomes useful in case of ionization of acids and bases, as mostly ionizations in chemical and biological systems occur in aqueous medium. Strong acids like perchloric acid HClO4, hydrochloric acid HCl, hydrobromic acid HBr, hydroiodic acid HI, nitric acid HNO3, and sulfuric acid H2SO4 are termed strong because they are almost completely dissociated into their constituent ions in an aqueous medium, thereby acting as proton H+ donors. Similarly, strong bases like lithium hydroxide LiOH, sodium hydroxide NaOH, potassium hydroxide KOH, cesium hydroxide CSOH, and barium hydroxide BaOH2 are almost completely dissociated into ions in an aqueous medium, giving hydroxyl ions OH-. According to Arrhenius' concept, they are strong acids and bases as they are able to completely dissociate and produce H3O+ and OH- ions respectively in the medium. Alternatively, the strength of an acid or base may also be gauged in terms of Bronsted-Lowry concept of acids and bases, wherein a strong acid means a good proton donor and a strong base implies a good proton acceptor. Consider the acid-base dissociation equilibrium of a weak acid HA. HA aqueous acid plus H2O liquid base gives H3O plus aqueous conjugate acid plus A minus aqueous conjugate base. In section 6.10.2, we saw that acid or base dissociation equilibrium is dynamic, involving a transfer of proton in forward and reverse directions. Now the question arises that if the equilibrium is dynamic, then with passage of time, which direction is favored? What is the driving force behind it? In order to answer these questions, we shall deal into the issue of comparing the strengths of the two acids or bases involved in the dissociation equilibrium. Consider the two acids HA and H3O+ present in the above mentioned acid dissociation equilibrium. We have to see which amongst them is a stronger proton donor. Whichever exceeds in its tendency of donating a proton over the other shall be termed as the stronger acid, and the equilibrium will shift in the direction of the weaker acid. Say, if HA is a stronger acid than H3O+, then HA will donate protons and not H3O+, and the solution will mainly contain A- and H3O+ ions. The equilibrium moves in the direction of formation of weaker acid and weaker base because the stronger acid donates a proton to the stronger base. It follows that as a strong acid dissociates completely in water, the resulting base formed would be very weak. That is, strong acids have very weak conjugate bases. Strong acids like perchloric acid HClO4, hydrochloric acid HCl, hydrobromic acid HBr, hydroiodic acid HI, nitric acid HNO3 and sulfuric acid H2SO4 will give conjugate base ions ClO4-, Cl, Br-, I-, NO3- and H2SO4-, which are much weaker bases than H2O. Similarly, a very strong base would give a very weak conjugate acid. On the other hand, a weak acid, say HA, is only partially dissociated in aqueous medium, and thus the solution mainly contains undissociated HA molecules. Typical weak acids are nitrous acid HNO2, hydrofluoric acid HF, and acetic acid CH3COOH. It should be noted that the weak acids have very strong conjugate bases. For example, NH2-, O2-, and H- are very good proton acceptors and thus much stronger bases than H2O. Certain water-soluble organic compounds like phenolphthalein and bromothiamol blue behave as weak acids and exhibit different colors in their acid HIN and conjugate base IN- forms. HIN aqueous, acid indicator color A, plus H2O liquid gives H3O plus aqueous conjugate acid and IN- aqueous conjugate base color B. Such compounds are useful as indicators in acid-base titrations and finding out H plus ion concentration. 6.11.1 The ionization constant of water and its ionic product. Some substances like water are unique in their ability of acting both as an acid and a base. We have seen this in case of water in section 6.10.2. In presence of an acid Ha, it accepts a proton and acts as the base, while in the presence of a base, B-, it acts as an acid by donating a proton. In pure water, one H2O molecule donates proton and acts as an acid, and another water molecule accepts a proton and acts as a base at the same time. The following equilibrium exists. H2O liquid acid plus H2O liquid base gives H3O plus aqueous conjugate acid plus OH minus aqueous conjugate base. The dissociation constant is represented by K equals H3O plus into OH minus divided by H2O, equation 6.26. The concentration of water is omitted from the denominator as water is a pure liquid and its concentration remains constant. H2O is incorporated within the equilibrium constant to give a new constant Kw, which is called the ionic product of water. Kw equals H plus into OH minus, equation 6.27. The concentration of H plus has been found out experimentally as 1 into 10 raised to minus 7 m at 298 K. And as dissociation of water produces equal number of H plus and OH minus ions, the concentration of hydroxyl ions OH minus equals H plus equals 1 into 10 raised to minus 7 m. Thus the value of Kw at 298 K, Kw equals H3O plus into OH minus equals 1 into 10 raised to minus 7 raised to 2 equals 1 into 10 raised to minus 14 m squared. Equation 6.28. The value of Kw is temperature dependent as it is an equilibrium constant. The density of pure water is 1000 grams per liter and its molar mass is 18 grams per mole. From this, the molarity of pure water can be given as H2O equals 1000 grams per liter into 1 mole per 18 grams equals 55.55 moles. Therefore, the ratio of dissociated water to that of undissociated water can be given as 10 raised to minus 7 divided by 55.55 equals 1.8 into 10 raised to minus 9 or approximately 2 into 10 raised to minus 9. Thus, equilibrium lies mainly towards undissociated water. We can distinguish acidic, neutral and basic aqueous solutions by the relative values of the H3O plus and OH minus concentrations. Acidic, H3O plus greater than OH minus. Neutral, H3O plus equals OH minus. Basic, H3O plus less than OH minus. 6.11.2 The pH scale. Hydronium ion concentration in molarity is more conveniently expressed on a logarithmic scale known as the pH scale. The pH of a solution is defined as the negative logarithm to base 10 of the activity AH plus of hydrogen ion. In dilute solutions less than 0.01 m, activity of hydrogen ion H plus is equal in magnitude to molarity represented by H plus. It should be noted that activity has no units and is defined as AH plus equals H plus per mole per liter. From the definition of pH, the following can be written. pH equals minus log AH plus equals minus log H plus per mole per liter. Thus, an acidic solution of HCl 10 raised to minus 2 m will have a pH of 2. Similarly, a basic solution of NaOH having OH minus equals 10 raised to minus 4 m and H3O plus equals 10 raised to minus 10 m will have a pH equal to 10. At 25 degrees Celsius, pure water has a concentration of hydrogen ions H plus equals 10 raised to minus 7 m. Hence, the pH of pure water is given as pH equals minus log of 10 raised to minus 7 equals 7. Acidic solutions possess a concentration of hydrogen ions H plus greater than 10 raised to minus 7 m, while basic solutions possess a concentration of hydrogen ions H plus less than 10 raised to minus 7 m. Thus, we can summarize that acidic solution has pH less than 7, basic solution has pH greater than 7, neutral solution has pH equal to 7. Now again consider the equation 6.28 at 298 K. Kw equals H3O plus into OH minus equals 10 raised to minus 14. Taking negative logarithm on both sides of equation, we obtain minus log Kw equals minus log H3O plus into OH minus equals minus log H3O plus minus log OH minus equals minus log 10 raised to minus 14. pKw equals pH plus pOH equals 14. Equation 6.29. Note that although Kw may change with temperature, the variations in pH with temperature are so small that we often ignore it. pKw is a very important quantity for aqueous solutions and controls the relative concentrations of hydrogen and hydroxyl ions as their product is a constant. It should be noted that as the pH scale is logarithmic, a change in pH by just 1 unit also means change in H plus by a factor of 10. Similarly, when the hydrogen ion concentration H plus changes by a factor of 100, the value of pH changes by 2 units. Now you can realize why the change in pH with temperature is often ignored. Measurement of pH of a solution is very essential as its value should be known when dealing with biological and cosmetic applications. The pH of a solution can be found roughly with the help of pH paper that has different color in solutions of different pH. Nowadays, pH paper is available with 4 strips on it. The different strips have different colors, figure 6.11, at the same pH. The pH in the range of 1 to 14 can be determined with an accuracy of approximately 0.5 using pH paper. For greater accuracy, pH meters are used. pH meter is a device that measures the pH-dependent electrical potential of the test solution within 0.001 precision. pH meters of the size of a writing pen are now available in the market. The pH of some very common substances are given in table 6.5, page 195. Problem 6.16. The concentration of hydrogen ion in a sample of soft drink is 3.8 into 10 raised to minus 3 m. What is its pH? Solution: pH equals minus log of 3.8 into 10 raised to minus 3 equals minus log 3.8 plus log 10 raised to minus 3 equals minus 0.58 plus minus 3 equals minus of minus 2.42 equals 2.42. Therefore, the pH of the soft drink is 2.42 and it can be inferred that it is acidic. Problem 6.17. Calculate pH of a 1 into 10 raised to minus 8 m solution of HCl. Solution: 2H2O liquid gives H3O plus aqueous plus OH minus aqueous. Kw equals OH minus into H3O plus equals 10 raised to minus 14. Let X equals OH minus equals H3O plus from H2O. The H3O plus concentration is generated 1. From the ionization of HCl dissolved, that is, HCl aqueous plus H2O liquid gives H3O plus aqueous plus Cl minus aqueous, and 2. From ionization of H2O. In these very dilute solutions, both sources of H3O plus must be considered. H3O plus equals 10 raised to minus 8 plus X. Kw equals 10 raised to minus 8 plus X into X equals 10 raised to minus 14, or X squared plus 10 raised to minus 8X minus 10 raised to minus 14 equals 0. OH minus equals X equals 9.5 into 10 raised to minus 8. So, POH equals 7.02 and pH equals 6.98. 6.11.3. Ionization constants of weak acids. Consider a weak acid HX that is partially ionized in the aqueous solution. The equilibrium can be expressed by HX aqueous plus H2O liquid gives H3O plus aqueous plus X minus aqueous. Initial concentration M, HX aqueous C, H3O plus aqueous 0, X minus aqueous 0. Let alpha be the extent of ionization change in moles. HX aqueous minus C alpha, H3O plus aqueous plus C alpha, X minus aqueous plus C alpha. Equilibrium concentration in moles: HX aqueous C minus C alpha, H3O plus aqueous C alpha, X minus aqueous C alpha. Here, C equals initial concentration of the undissociated acid HX at time t equals 0. Alpha equals extent up to which HX is ionized into ions. Using these notations, we can derive the equilibrium constant for the above discussed acid dissociation equilibrium. Ka equals C squared alpha squared divided by C into 1 minus alpha equals C alpha squared divided by 1 minus alpha. Ka is called the dissociation or ionization constant of acid HX. It can be represented alternatively in terms of molar concentration as follows. Ka equals H plus into X minus divided by H into X. Equation 6.30. At a given temperature T, Ka is a measure of the strength of the acid HX, that is, larger the value of Ka, the stronger is the acid. Ka is a dimensionless quantity with the understanding that the standard state concentration of all species is 1 mole. The values of the ionization constants of some selected weak acids are given in table 6.6. The pH scale for the hydrogen ion concentration has been so useful that, besides pKw, it has been extended to other species and quantities. Thus we have pKa equals minus log Ka, equation 6.31. Knowing the ionization constant Ka of an acid and its initial concentration C, it is possible to calculate the equilibrium concentration of all species and also the degree of ionization of the acid and the pH of the solution. A general stepwise approach can be adopted to evaluate the pH of the weak electrolyte as follows. Step 1. The species present before dissociation are identified as Bronsted-Lowry acids or bases. Step 2. Balanced equations for all possible reactions, that is, with a species acting both as acid as well as base, are written. Step 3. The reaction with the higher Ka is identified as the primary reaction, whilst the other is a subsidiary reaction. Step 4. Enlist in a tabular form the following values for each of the species in the primary reaction. A. Initial concentration C. B. Change in concentration on proceeding to equilibrium in terms of alpha, degree of ionization. C. Equilibrium concentration. Step 5. Substitute equilibrium concentrations into equilibrium constant equation for principal reaction and solve for alpha. Step 6. Calculate the concentration of species in principal reaction. Step 7. Calculate pH equals minus log H3O+. The above mentioned methodology has been elucidated in the following examples. Problem 6.18. The ionization constant of HF is 3.2 into 10 raised to minus 4. Calculate the degree of dissociation of HF in its 0.02 m solution. Calculate the concentration of all species present, H3O+, F-, and HF, in the solution and its pH. Solution. The following proton transfer reactions are possible. 1. HF plus H2O gives H3O plus F-, Ka equals 3.2 into 10 raised to minus 4. 2. H2O plus H2O gives H3O plus OH minus. Kw equals 1 into 10 raised to minus 14. As Ka is greater than Kw, 1 is the principal reaction. HF plus H2O gives H3O plus F-. Initial concentration M, HF 0.02, H3O plus 0, F minus 0. As Ka greater than Kw, 1 is the principal reaction. HF plus H2O gives H3O plus F minus. Initial concentration in moles, HF 0.02, H3O plus 0, F minus 0. Change in moles, HF minus 0.02 alpha, H3O plus 0.02 alpha, F minus plus 0.02 alpha. Equilibrium concentration in moles, HF 0.02 minus 0.02 alpha, H3O plus 0.02 alpha, F minus 0.02 alpha. Substituting equilibrium concentrations in the equilibrium reaction for principal reaction gives Ka equals 0.02 alpha squared divided by 0.02 minus 0.02 alpha equals 0.02 alpha squared divided by 1 minus alpha equals 3.2 into 10 raised to minus 4. We obtain the following quadratic equation: alpha squared plus 1.6 into 10 raised to minus 2 alpha minus 1.6 into 10 raised to minus 2 equals 0. The quadratic equation in alpha can be solved, and the two values of the roots are alpha equals plus 0.12 and minus 0.12. The negative root is not acceptable, and hence alpha equals 0.12. This means that the degree of ionization alpha equals 0.12. Then equilibrium concentrations of other species, namely HF, F minus and H3O plus, are given by H3O plus equals F minus equals C into alpha equals 0.02 into 0.12 equals 2.4 into 10 raised to minus 3 moles. HF equals C into 1 minus alpha equals 0.02 into 1 minus 0.12 equals 17.6 into 10 raised to minus 3 m. pH equals minus log of H plus equals minus log of 2.4 into 10 raised to minus 3 equals 2.62. Problem 6.19. The pH of 0.1 m monobasic acid is 4.50. Calculate the concentration of species H plus, A minus and HA at equilibrium. Also determine the value of Ka and pKa of the monobasic acid. Solution: pH equals minus log H plus. Therefore, H plus equals 10 raised to minus pH equals 10 raised to minus 4.5 equals 3.16 into 10 raised to minus 5. H plus equals A minus equals 3.16 into 10 raised to minus 5. Thus, Ka equals H plus into A minus divided by HA. HA at equilibrium equals 0.1 minus 3.16 into 10 raised to minus 5, approximately equal to 0.1. Ka equals 3.16 into 10 raised to minus 5 raised to 2 divided by 0.1 equals 1 into 10 raised to minus 8. pKa equals minus log of 10 raised to minus 8 equals 8. Alternatively, percent dissociation is another useful method for measure of strength of a weak acid and is given as percent dissociation equals HA dissociated divided by HA initial into 100%. Equation 6.32. Problem 6.20. Calculate the pH of 0.08 m solution of hypochlorous acid HOCl. The ionization constant of the acid is 2.5 into 10 raised to minus 5. Determine the percent dissociation of HOCl. Solution: HOCl aqueous plus H2O liquid gives H3O plus aqueous plus ClO minus aqueous. Initial concentration in moles: HOCl 0.08, H3O plus 0, ClO minus 0. Change to reach equilibrium concentration in moles: HOCl aqueous minus X, H3O plus aqueous plus X, ClO minus aqueous plus X. Equilibrium concentration in moles: HOCl aqueous 0.08 minus X, H3O plus aqueous X, ClO minus aqueous X. Ka equals H3O plus into ClO minus divided by HOCl equals X squared divided by 0.08 minus X. As X less than 0.08, therefore 0.08 minus X approximately equals 0.08. X squared divided by 0.08 equals 2.5 into 10 raised to minus 5. X squared equals 2 into 10 raised to minus 6. Thus, X equals 1.41 into 10 raised to minus 3. H plus equals 1.41 into 10 raised to minus 3 m. Therefore, percent dissociation equals HOCl dissociated divided by HOCl initial into 100 equals 1.41 into 10 raised to minus 3 into 10 squared divided by 0.08 equals 1.76%. pH equals minus log of 1.41 into 10 raised to minus 3 equals 2.85. 6.11.4 Ionization of weak bases. The ionization of base MOH can be represented by equation MOH aqueous gives M plus aqueous plus OH minus aqueous. In a weak base, there is partial ionization of MOH into M plus and OH minus. The case is similar to that of acid dissociation equilibrium. The equilibrium constant for base ionization is called base ionization constant and is represented by Kb. It can be expressed in terms of concentration in molarity of various species in equilibrium by the following equation. Kb equals M plus into OH minus divided by MOH. Equation 6.33. Alternatively, if C equals initial concentration of base and alpha equals degree of ionization of base, that is, the extent to which the base ionizes. When equilibrium is reached, the equilibrium constant can be written as Kb equals C alpha the whole squared divided by C into 1 minus alpha equals C alpha squared divided by 1 minus alpha. The values of the ionization constants of some selected weak bases Kb are given in table 6.7. Many organic compounds like amines are weak bases. Amines are derivatives of ammonia in which one or more hydrogen atoms are replaced by another group. For example, methylamine, codeine, quinine, and nicotine all behave as very weak bases due to their very small Kb. Ammonia produces OH- in aqueous solution. NH3 aqueous plus H2O liquid gives NH4 plus aqueous plus OH- aqueous. The pH scale for the hydrogen ion concentration has been extended to get pKb equals minus log of Kb, equation 6.34. Problem 6.21. The pH of 0.004 m hydrazine solution is 9.7. Calculate its ionization constant Kb and pKb. Solution: NH2 plus H2O gives NH2 NH3 plus OH-. From the pH we can calculate the hydrogen ion concentration. Knowing hydrogen ion concentration and the ionic product of water, we can calculate the concentration of hydroxyl ions. Thus we have H plus equals anti-log minus pH equals anti-log minus 9.7 equals 1.67 into 10 raised to minus 10. OH minus equals Kw divided by H plus equals 1 into 10 raised to minus 14 divided by 1.67 into 10 raised to minus 10 equals 5.98 into 10 raised to minus 5. The concentration of the corresponding hydrazinium ion is also the same as that of hydroxyl ion. The concentration of both these ions is very small, so the concentration of the undissociated base can be taken equal to 0.004 m. Thus, Kb equals NH2 NH3 plus into OH minus divided by NH2 NH2 equals 5.98 into 10 raised to minus 5 raised to 2 divided by 0.004 equals 8.96 into 10 raised to minus 7. pKb equals minus log Kb equals minus log of 8.96 into 10 raised to minus 7 equals 6.04. Problem 6.22. Calculate the pH of the solution in which 0.2 m NH4Cl and 0.1 m NH3 are present. The pKb of ammonia solution is 4.75. Solution: NH3 plus H2O gives NH4 plus OH minus. The ionization constant of NH3 Kb equals anti-log minus pKb, that is Kb equals 10 raised to minus 4.75 equals 1.77 into 10 raised to minus 5 m. NH3 plus H2O gives NH4 plus OH minus. Initial concentration in moles: NH3 0.10, NH4 plus 0.20, OH minus 0. Change to reach equilibrium in moles: NH3 minus X, NH4 plus X, OH minus plus X. At equilibrium in moles: NH3 0.10 minus X, NH4 plus 0.20 plus X, OH minus X. Kb equals NH4 plus into OH minus divided by NH3 equals 0.20 plus X into X divided by 0.1 minus X equals 1.77 into 10 raised to minus 5. As Kb is small, we can neglect X in comparison to 0.1 m and 0.2 m. Thus, OH minus equals X equals 0.88 into 10 raised to minus 5. Therefore, H plus equals 1.12 into 10 raised to minus 9. pH equals minus log H plus equals 8.95. 6.11.5 Relation between Ka and Kb. As seen earlier in this chapter, Ka and Kb represent the strength of an acid and a base, respectively. In case of a conjugate acid-base pair, they are related in a simple manner so that if one is known, the other can be deduced. Considering the example of NH4 plus and NH3, we see NH4 plus aqueous plus H2O liquid gives H3O plus aqueous plus NH3 aqueous. Ka equals H3O plus into NH3 divided by NH4 plus equals 5.6 into 10 raised to minus 10. NH3 aqueous plus H2O liquid gives NH4 plus aqueous plus OH minus aqueous. Kb equals NH4 plus into OH minus divided by NH3 equals 1.8 into 10 raised to minus 5. Net 2H2O liquid gives H3O plus aqueous plus OH minus aqueous. Kw equals H3O plus into OH minus equals 1 into 10 raised to minus 14 m, where Ka represents the strength of NH4 plus as an acid and Kb represents the strength of NH3 as a base. It can be seen from the net reaction that the equilibrium constant is equal to the product of equilibrium constants Ka and Kb for the reactions added. Thus, Ka into Kb equals H3O plus into NH3 divided by NH4 plus into NH4 plus into OH minus divided by NH3 equals H3O plus into OH minus equals Kw equals 5.6 into 10 raised to minus 10 into 1.8 into 10 raised to minus 5 equals 1 into 10 raised to minus 14 m. This can be extended to make a generalization. The equilibrium constant for a net reaction obtained after adding two or more reactions equals the product of the equilibrium constants for individual reactions. K net equals K1 into K2 into etc. Equation 6.35. Similarly, in case of a conjugate acid-base pair, Ka into Kb equals Kw. Equation 6.36. Knowing one, the other can be obtained. It should be noted that a strong acid will have a weak conjugate base and vice versa. Alternatively, the above expression Kw equals Ka into Kb can also be obtained by considering the base dissociation equilibrium reaction B aqueous plus H2O liquid gives BH plus aqueous plus OH minus aqueous. Kb equals BH plus into OH minus divided by B. As the concentration of water remains constant, it has been omitted from the denominator and incorporated within the dissociation constant. Then multiplying and dividing the above expression by H plus, we get Kb equals BH plus into OH minus into H plus divided by B into H plus equals OH minus into H plus into BH plus divided by B into H plus equals Kw divided by Ka, or Ka into Kb equals Kw. It may be noted that if we take negative logarithm on both sides of the equation, then pK values of the conjugate acid and base are related to each other by the equation pKa plus pKb equals pKw equals 14 at 298 K. Problem 6.23. Determine the degree of ionization and pH of a 0.05 m of ammonia solution. The ionization constant of ammonia can be taken from table 6.7. Also, calculate the ionization constant of the conjugate acid of ammonia. Solution. The ionization of NH3 in water is represented by equation NH3 plus H2O gives NH4 plus OH minus. We use equation 6.33 to calculate hydroxyl ion concentration. OH minus equals C alpha equals 0.05 alpha. Kb equals 0.05 alpha squared divided by 1 minus alpha. The value of alpha is small. Therefore, the quadratic equation can be simplified by neglecting alpha in comparison to 1 in the denominator on right hand side of the equation. Thus, Kb equals C alpha squared, or alpha equals square root of 1.77 into 10 raised to minus 5 divided by 0.05 equals 0.018. OH minus equals C alpha equals 0.05 into 0.018 equals 9.4 into 10 raised to minus 4 m. H plus equals Kw divided by OH minus equals 10 raised to minus 14 divided by 9.4 into 10 raised to minus 4 equals 1.06 into 10 raised to minus 11. pH equals minus log of 1.06 into 10 raised to minus 11 equals 10.97. Now, using the relation for conjugate acid-base pair Ka into Kb equals Kw, using the value of Kb of NH3 from table 6.7, we can determine the concentration of conjugate acid NH4 plus. Ka equals Kw divided by Kb equals 10 raised to minus 14 divided by 1.77 into 10 raised to minus 5 equals 5.64 into 10 raised to minus 10. 6.11.6 Di and polybasic acids and di and polyacidic bases. Some of the acids like oxalic acid, sulfuric acid and phosphoric acids have more than one ionizable proton per molecule of the acid. Such acids are known as polybasic or polyprotic acids. The ionization reactions, for example, for a dibasic acid H2X are represented by the equations. H2X aqueous gives H plus aqueous plus HX minus aqueous. HX minus aqueous gives H plus aqueous plus H2 minus aqueous. And the corresponding equilibrium constants are given by Ka1 equals H plus into Hx minus divided by H2x and Ka2 equals H plus into X2 minus divided by Hx minus. Here Ka1 and Ka2 are called the first and second ionization constants respectively of the acid H2X. Similarly, for tribasic acids like H3PO4, we have three ionization constants. The values of the ionization constants for some common polyprotic acids are given in table 6.8. It can be seen that higher order ionization constants Ka2, Ka3 are smaller than the lower order ionization constant Ka1 of a polyprotic acid. The reason for this is that it is more difficult to remove a positively charged proton from a negative ion due to electrostatic forces. This can be seen in the case of removing a proton from the uncharged H2CO3 as compared from a negatively charged HCO3-. Similarly, it is more difficult to remove a proton from a doubly charged HPO4-2- anion as compared to H2PO4-. Polyprotic acid solutions contain a mixture of acids like H2A, HA- and A2- in case of a diprotic acid. H2A being a strong acid, the primary reaction involves the dissociation of H2A and H3O+ in the solution comes mainly from the first dissociation step. 6.11.7 Factors affecting acid strength. Having discussed quantitatively the strengths of acids and bases, we come to a stage where we can calculate the pH of a given acid solution. But the curiosity rises about why should some acids be stronger than others? What factors are responsible for making them stronger? The answer lies in its being a complex phenomenon. But broadly speaking, we can say that the extent of dissociation of an acid depends on the strength and polarity of the HA bond. In general, when strength of HA bond decreases, that is, the energy required to break the bond decreases, HA becomes a stronger acid. Also, when the HA bond becomes more polar, that is, the electronegativity difference between the atoms H and A increases, and there is marked charge separation, cleavage of the bond becomes easier, thereby increasing the acidity. But it should be noted that while comparing elements in the same group of the periodic table, HA bond strength is a more important factor in determining acidity than its polar nature. As the size of A increases down the group, HA bond strength decreases, and so the acid strength increases. For example, HF less than HCl less than HBr less than HI. Size increases, acid strength increases. Similarly, H2S is stronger acid than H2O. But when we discuss elements in the same row of the periodic table, HA bond polarity becomes the deciding factor for determining the acid strength. As the electronegativity of A increases, the strength of the acid also increases. For example, CH4 less than NH3 less than H2O less than HF. Electronegativity of A increases, acid strength increases. 6.11.8 Common ion effect in the ionization of acids and bases. Consider an example of acetic acid dissociation equilibrium represented as CH3COOH aqueous giving H plus aqueous plus CH3COO minus aqueous, or HAC aqueous gives H plus aqueous plus AC minus aqueous. Ka equals H plus into AC minus divided by HAC. Addition of acetate ions to an acetic acid solution results in decreasing the concentration of hydrogen ions H plus. Also, if H plus ions are added from an external source, then the equilibrium moves in the direction of undissociated acetic acid, that is, in a direction of reducing the concentration of hydrogen ions H plus. This phenomenon is an example of common ion effect. It can be defined as a shift in equilibrium on adding a substance that provides more of an ionic species already present in the dissociation equilibrium. Thus, we can say that common ion effect is a phenomenon based on the Le Chatelier's principle discussed in section 6.8. In order to evaluate the pH of the solution resulting on addition of 0.05 m acetate ion to 0.05 m acetic acid solution, we shall consider the acetic acid dissociation equilibrium once again. HAC aqueous gives H plus aqueous plus AC minus aqueous. Initial concentration in moles: HAC aqueous 0.05, H plus aqueous 0, AC minus aqueous 0.05. Let X be the extent of ionization of acetic acid. Change in concentration in moles: HAC aqueous minus X, H plus aqueous plus X, AC minus aqueous plus X. Equilibrium concentration M: HAC aqueous 0.05 minus X, H plus aqueous X, AC minus aqueous 0.05 plus X. Therefore, Ka equals H plus into AC minus divided by HAC equals 0.05 plus X into X divided by 0.05 minus X. As Ka is small for a very weak acid, X less than 0.05. Hence, 0.05 plus X approximately equal to 0.05 minus X, which is approximately equal to 0.05. Thus, 1.8 into 10 raised to minus 5 equals X into 0.05 plus X divided by 0.05 minus X equals X into 0.05 divided by 0.05 equals X equals H plus equals 1.8 into 10 raised to minus 5 m. pH equals minus log of 1.8 into 10 raised to minus 5 equals 4.74. Problem 6.24. Calculate the pH of a 0.10 m ammonia solution. Calculate the pH after 50 ml of this solution is treated with 25 ml of 0.10 m HCl. The dissociation constant of ammonia Kb equals 1.77 into 10 raised to minus 5. Solution: NH3 plus H2O gives NH4 plus OH minus. Kb equals NH4 plus into OH minus divided by NH3 equals 1.77 into 10 raised to minus 5. Before neutralization, NH4 plus equals OH minus equals X. NH3 equals 0.10 minus X approximately equal to 0.10. X squared divided by 0.10 equals 1.77 into 10 raised to minus 5. Thus, X equals 1.33 into 10 raised to minus 3 equals OH minus. Therefore, H plus equals Kw divided by OH minus equals 10 raised to minus 14 divided by 1.33 into 10 raised to minus 3 equals 7.51 into 10 raised to minus 12. pH equals minus log of 7.5 into 10 raised to minus 12 equals 11.12. On addition of 25 ml of 0.1 m HCl solution, that is 2.5 m mole of HCl to 50 ml of 0.1 m ammonia solution, that is 5 m mole of NH3, 2.5 m mole of ammonia molecules are neutralized. The resulting 75 ml solution contains the remaining unneutralized 2.5 m mole of NH3 molecules and 2.5 m mole of NH4 plus. NH3 2.5 plus HCl 2.5 gives NH4 plus 0 plus Cl minus 0. At equilibrium, NH3 0, HCl 0, NH4 plus 2.5, Cl minus 2.5. The resulting 75 ml of solution contains 2.5 m mole of NH4 plus ions, that is 0.033 m, and 2.5 m mole, that is 0.033 m of unneutralized NH3 molecules. This NH3 exists in the following equilibrium. NH4OH gives NH4 plus OH minus. NH4OH 0.033 m minus Y, NH4 plus Y, OH minus Y, where Y equals OH minus equals NH4 plus. The final 75 ml solution after neutralization already contains 2.5 m mole NH4 plus ions, that is 0.033 m. Thus, total concentration of NH4 plus ions is given as NH4 plus equals 0.033 plus Y. As Y is small, NH4OH approximately equals 0.033 m and NH4 plus approximately equals 0.033 m. We know Kb equals NH4 plus OH minus divided by NH4OH equals Y into 0.033 divided by 0.033 equals 1.77 into 10 raised to minus 5 m. Thus, Y equals 1.77 into 10 raised to minus 5 equals OH minus. H plus equals 10 raised to minus 14 divided by 1.77 into 10 raised to minus 5 equals 0.56 into 10 raised to minus 9. Hence, pH equals 9.24. 6.11.9 Hydrolysis of salts and the pH of their solutions. Salts formed by the reactions between acids and bases in definite proportions undergo ionization in water. The cations or anions formed on ionization of salts either exist as hydrated ions in aqueous solutions or interact with water to reform corresponding acids or bases depending upon the nature of salts. The later process of interaction between water and cations or anions or both of salts is called hydrolysis. The pH of the solution gets affected by this interaction. The cations, example Na+, K+, Ca2+, Ba2+, etc., of strong bases and anions, example Cl-, Br-, NO3-, ClO4-, etc., of strong acids simply get hydrated but do not hydrolyze, and therefore the solutions of salts formed from strong acids and bases are neutral, that is, their pH is 7. However, the other category of salts do undergo hydrolysis. We now consider the hydrolysis of the salts of the following types. 1. Salts of weak acid and strong base, example CH3COONa. 2. Salts of strong acid and weak base, example NH4Cl. And 3. Salts of weak acid and weak base, example CH3COONH4. In the first case, CH3COONa being a salt of weak acid, CH3COOH and strong base NaOH gets completely ionized in aqueous solution. CH3COONa aqueous gives CH3COO minus aqueous plus Na plus aqueous. Acetate ion thus formed undergoes hydrolysis in water to give acetic acid and OH minus ions. CH3COO minus aqueous plus H2O liquid gives CH3COOH aqueous plus OH minus aqueous. Acetic acid being a weak acid, Ka equals 1.8 into 10 raised to minus 5, remains mainly unionized in solution. This results in increase of OH minus ion concentration in solution, making it alkaline. The pH of such a solution is more than 7. Similarly, NH4Cl formed from weak base NH4OH and strong acid HCl in water dissociates completely. NH4Cl aqueous gives NH4 plus aqueous plus Cl minus aqueous. Ammonium ions undergo hydrolysis with water to form NH4OH and H plus ions. NH4 plus aqueous plus H2O liquid gives NH4OH aqueous plus H plus aqueous. Ammonium hydroxide is a weak base. Kb equals 1.77 into 10 raised to minus 5 and therefore remains almost unionized in solution. This results in increase of H plus ion concentration in solution, making the solution acidic. Thus, the pH of NH4Cl solution in water is less than 7. Consider the hydrolysis of CH3COONH4 salt formed from weak acid and weak base. The ions formed undergo hydrolysis as follows. CH3COO minus plus NH4 plus H2O gives CH3COOH plus NH4OH. CH3COOH and NH4OH also remain into partially dissociated form. CH3COOH gives CH3COO minus plus H plus. NH4OH gives NH4 plus OH minus. H2O gives H plus OH minus. Without going into detailed calculation, it can be said that degree of hydrolysis is independent of concentration of solution, and pH of such solutions is determined by their pK values. pH equals 7 plus half into, within parenthesis, pKa minus pKb. Equation 6.38. The pH of solution can be greater than 7 if the difference is positive, and it will be less than 7 if the difference is negative. Problem 6.25. The pKa of acetic acid and pKb of ammonium hydroxide are 4.76 and 4.75 respectively. Calculate the pH of ammonium acetate solution. Solution: pH equals 7 plus half of pKa minus pKb. 7 plus half of 4.76 minus 4.75 equals 7 plus half of 0.01 equals 7 plus 0.005 equals 7.005. 6.12. Buffer solutions. Many body fluids, example blood or urine, have definite pH, and any deviation in their pH indicates malfunctioning of the body. The control of pH is also very important in many chemical and biochemical processes. Many medical and cosmetic formulations require that these be kept and administered at a particular pH. The solutions which resist change in pH on dilution or with the addition of small amounts of acid or alkali are called buffer solutions. Buffer solutions of known pH can be prepared from the knowledge of pKa of the acid or pKb of base, and by controlling the ratio of the salt and acid or salt and base. A mixture of acetic acid and sodium acetate acts as buffer solution around pH 4.75, and a mixture of ammonium chloride and ammonium hydroxide act as a buffer around pH 9.25. You will learn more about buffer solutions in higher classes. 6.12.1. Designing buffer solution. Knowledge of pKa, pKb and equilibrium constant help us to prepare the buffer solution of known pH. Let us see how we can do this. Preparation of acidic buffer. To prepare a buffer of acidic pH, we use weak acid and its salt formed with strong base. We develop the equation relating the pH, the equilibrium constant, Ka of weak acid, and ratio of concentration of weak acid and its conjugate base. For the general case where the weak acid Ha ionizes in water, Ha plus H2O gives H3O plus A minus, for which we can write the expression Ka equals H3O plus into A minus divided by HA. Rearranging the expression, we have H3O plus equals Ka into HA divided by A minus. Taking logarithm on both the sides and rearranging the terms, we get pKa equals pH minus log of A minus divided by HA, or pH equals pKa plus log of A minus divided by HA. Equation 6.39. pH equals pKa plus log of conjugate base A minus divided by acid HA. Equation 6.40. The expression 6.40 is known as Henderson-Hasselbalch equation. The quantity A minus divided by HA is the ratio of concentration of conjugate base anion of the acid and the acid present in the mixture. Since acid is a weak acid, it ionizes to a very little extent, and concentration of HA is negligibly different from concentration of acid taken to form buffer. Also, most of the conjugate base A minus comes from the ionization of salt of the acid. Therefore, the concentration of conjugate base will be negligibly different from the concentration of salt. Thus, equation 6.40 takes the form pH equals pKa plus log of salt divided by acid. In the equation 6.39, if the concentration of A minus is equal to the concentration of HA, then pH equals pKa because value of log 1 is 0. Thus, if we take molar concentration of acid and salt conjugate base same, the pH of the buffer solution will be equal to the pKa of the acid. So, for preparing the buffer solution of the required pH, we select that acid whose pKa is close to the required pH. For acetic acid, pKa value is 4.76. Therefore, pH of the buffer solution formed by acetic acid and sodium acetate taken in equal molar concentration will be around 4.76. A similar analysis of a buffer made with a weak base and its conjugate acid leads to the result POH equals pKb plus log of conjugate acid BH plus divided by base B. Equation 6.41. pH of the buffer solution can be calculated by using the equation pH plus POH equals 14. We know that pH plus POH equals pKw and pKa plus pKb equals pKw. On putting these values in equation 6.41, it takes the form as follows. pKw minus pH equals pKw minus pKa plus log conjugate acid BH plus divided by base B, or pH equals pKa plus log conjugate acid BH plus divided by base B, equation 6.42. If molar concentration of base and its conjugate acid cation is same, then pH of the buffer solution will be the same as pKa for the base. pKa value for ammonia is 9.25. Therefore, a buffer of pH close to 9.25 can be obtained by taking ammonia solution and ammonium chloride solution of same molar concentration. For a buffer solution formed by ammonium chloride and ammonium hydroxide, equation 6.42 becomes pH equals 9.25 plus log of conjugate acid BH plus divided by base B. pH of the buffer solution is not affected by dilution because the ratio under the logarithmic term remains unchanged. 6.13 Solubility equilibria of sparingly soluble salts. We have already known that the solubility of ionic solids in water varies a great deal. Some of these, like calcium chloride, are so soluble that they are hygroscopic in nature and even absorb water vapor from atmosphere. Others, such as lithium fluoride, have so little solubility that they are commonly termed as insoluble. The solubility depends on a number of factors, important amongst which are the lattice enthalpy of the salt and the solvation enthalpy of the ions in a solution. For a salt to dissolve in a solvent, the strong forces of attraction between its ions, lattice enthalpy, must be overcome by the ion-solvent interactions. The solvation enthalpy of ions is referred to in terms of solvation which is always negative, that is, energy is released in the process of solvation. The amount of solvation enthalpy depends on the nature of the solvent. In case of a non-polar, covalent solvent, solvation enthalpy is small and hence not sufficient to overcome lattice enthalpy of the salt. Consequently, the salt does not dissolve in non-polar solvent. As a general rule, for a salt to be able to dissolve in a particular solvent, its solvation enthalpy must be greater than its lattice enthalpy so that the latter may be overcome by former. Each salt has its characteristic solubility, which depends on temperature. We classify salts on the basis of their solubility in the following three categories. Category 1 Soluble, solubility greater than 0.1 m. Category 2 Slightly soluble, 0.01 m less than solubility less than 0.1 m. Category 3 Sparingly soluble, solubility less than 0.01 m. We shall now consider the equilibrium between the sparingly soluble ionic salt and its saturated aqueous solution. 6.13.1 Solubility product constant. Let us now have a solid like barium sulfate in contact with its saturated aqueous solution. The equilibrium between the undissolved solid and the ions in a saturated solution can be represented by the equation BaSO4 solid saturated solution in water gives Ba2 plus aqueous plus SO4 2 minus aqueous and reverse. The equilibrium constant is given by the equation K equals Ba2 plus into SO4 2 minus divided by BaSO4. For a pure solid substance, the concentration remains constant and we can write Ksp equals K into BaSO4 equals Ba2 plus into SO4 2 minus. Equation 6.43. We call Ksp the solubility product constant or simply solubility product. The experimental value of Ksp in above equation at 298 K is 1.1 into 10 raised to minus 10. This means that for solid barium sulfate in equilibrium, with its saturated solution, the product of the concentrations of barium and sulfate ions is equal to its solubility product constant. The concentrations of the two ions will be equal to the molar solubility of the barium sulfate. If molar solubility is S, then 1.1 into 10 raised to minus 10 equals S into S equals S squared, or S equals 1.05 into 10 raised to minus 5. Thus, molar solubility of barium sulfate will be equal to 1.05 into 10 raised to minus 5 moles per liter. A salt may give on dissociation two or more than two anions and cations carrying different charges. For example, consider a salt like zirconium phosphate of molecular formula Zr3 raised to 4 plus PO4 4 raised to 3 minus. It dissociates into 3 zirconium cations of charge plus 4 and 4 phosphate anions of charge minus 3. If the molar solubility of zirconium phosphate is S, then it can be seen from the stoichiometry of the compound that Zr raised to 4 plus equals 3 into S, and PO4 raised to 3 minus equals 4 into S, and KSP equals 3S raised to 3 into 4S raised to 4 equals 6912 S raised to 7, or S equals KSP divided by 3 cube into 4 raised to 4 the whole raised to 1 by 7 equals KSP divided by 6912 raised to 1 by 7. A solid salt of the general formula mx raised to p plus x y raised to q minus with molar solubility S in equilibrium with its saturated solution may be represented by the equation mx xy solid gives x into m raised to p plus aqueous plus y into x raised to q minus aqueous, where x into p plus equals y into q minus, and its solubility product constant is given by KSP equals m raised to p plus raised to x into x raised to q minus raised to y equals x into s raised to x into y into s raised to y. Equation 6.44 equals x raised to x into y raised to y into s raised to x plus y. S raised to x plus y equals KSP divided by x raised to x into y raised to y. S is equal to KSP divided by x raised to x into y raised to y the whole raised to 1 divided by x plus y. Equation 6.45. The term KSP in equation is given by QSP, section 6.6.2, when the concentration of one or more species is not the concentration under equilibrium. Obviously, under equilibrium conditions, KSP equals QSP, but otherwise, it gives the direction of the processes of precipitation or dissolution. The solubility product constants of a number of common salts at 298 K are given in table 6.9. Problem 6.26. Calculate the solubility of A2X3 in pure water assuming that neither kind of ion reacts with water. The solubility product of A2X3 Ksp equals 1.1 into 10 raised to minus 23. Solution: A2X3 gives 2a raised to 3 plus 3x raised to 2 minus. Ksp equals a raised to 3 plus the whole squared into x raised to 2 minus the whole cube equals 1.1 into 10 raised to minus 23. If S equals solubility of A2X3, then a raised to 3 plus equals 2s, x raised to 2 minus equals 3s. Therefore, Ksp equals 2s raised to 2 into 3s raised to 3 equals 108 s raised to 5 equals 1.1 into 10 raised to minus 23. Thus, s raised to 5 equals 1 into 10 raised to minus 25. S equals 1 into 10 raised to minus 5 moles per liter. Problem 6.27. The values of Ksp of two sparingly soluble salts NiOH2 and AgCN are 2 into 10 raised to minus 15 and 6 into 10 raised to minus 17 respectively. Which salt is more soluble? Explain. Solution: AgCN gives Ag plus Cn minus. Ksp equals Ag plus into Cn minus equals 6 into 10 raised to minus 17. NiOH2 gives Ni raised to 2 plus 2OH minus. Ksp equals Ni raised to 2 plus into OH minus raised to 2 equals 2 into 10 raised to minus 15. Let Ag plus equals S1, then Cn minus equals S1. Let Ni raised to 2 plus equals S2, then OH minus equals 2S2. S1 squared equals 6 into 10 raised to minus 17. S1 equals 7.8 into 10 raised to minus 9. S2 into 2S2 squared equals 2 into 10 raised to minus 15. S2 equals 0.58 into 10 raised to minus 4. NiOH2 is more soluble than AgCN. 6.13.2 Common ion effect on solubility of ionic salts. It is expected from Le Chatelier's principle that if we increase the concentration of any one of the ions, it should combine with the ion of its opposite charge, and some of the salt will be precipitated till once again Ksp equals Qsp. Similarly, if the concentration of one of the ions is decreased, more salt will dissolve to increase the concentration of both the ions till once again Ksp equals Qsp. This is applicable even to soluble salts like sodium chloride, except that due to higher concentrations of the ions, we use their activities instead of their molarities in the expression for Qsp. Thus, if we take a saturated solution of sodium chloride and pass HCl gas through it, then sodium chloride is precipitated due to increased concentration activity of chloride ion available from the dissociation of HCl. Sodium chloride thus obtained is of very high purity, and we can get rid of impurities like sodium and magnesium sulfates. The common ion effect is also used for almost complete precipitation of a particular ion as its sparingly soluble salt with very low value of solubility product for gravimetric estimation. Thus, we can precipitate silver ion as silver chloride, ferric ion as its hydroxide or hydrated ferric oxide, and barium ion as its sulfate for quantitative estimations. Problem 6.28. Calculate the molar solubility of NiOH2 in 0.10 m NaOH. The ionic product of NiOH2 is 2 into 10 raised to minus 15. Solution. Let the solubility of NiOH2 be equal to S. Dissolution of S mole per liter of NiOH2 provides S mole per liter of Ni raised to 2 plus and 2S mole per liter of OH minus, but the total concentration of OH minus equals 0.10 plus 2S moles per liter because the solution already contains 0.10 moles per liter of OH minus from NaOH. Ksp equals 2 into 10 raised to minus 15 equals Ni raised to 2 plus into OH minus raised to 2 equals S into within parenthesis 0.10 plus 2S parenthesis closed raised to 2. As Ksp is small, 2S is less than 0.10, thus 0.10 plus 2S is approximately equal to 0.10. Hence, 2 into 10 raised to minus 15 equals S into 0.10 squared. S equals 2 into 10 raised to minus 13 m equals Ni raised to 2 plus. The solubility of salts of weak acids like phosphates increases at lower pH. This is because at lower pH, the concentration of the anion decreases due to its protonation. This in turn increases the solubility of the salt so that Ksp equals Qsp. We have to satisfy two equilibria simultaneously, that is, Ksp equals m plus into x minus. Hx aqueous gives H plus aqueous plus X minus aqueous. Ka equals H plus aqueous into X minus aqueous divided by HX aqueous. X minus divided by HX equals Ka divided by H plus. Taking inverse of both sides and adding 1, we get Hx divided by X minus plus 1 equals H plus divided by Ka plus 1. Hx plus H minus divided by X minus equals H plus Ka divided by Ka. Now again taking inverse, we get X minus divided by X minus plus Hx equals F equals Ka divided by Ka plus H plus, and it can be seen that F decreases as pH decreases. If S is the solubility of the salt at a given pH, then Ksp equals S into Fs equals S squared into Ka divided by Ka plus H plus, and S equals Ksp into H plus Ka divided by Ka raised to 1 by 2. Equation 6.46. Thus, solubility S increases with increase in H plus or decrease in pH. Summary. When the number of molecules leaving the liquid to vapor equals the number of molecules returning to the liquid from vapor, equilibrium is said to be attained and is dynamic in nature. Equilibrium can be established for both physical and chemical processes, and at this stage, rate of forward and reverse reactions are equal. Equilibrium constant Kc is expressed as the concentration of products divided by reactants, each term raised to the stoichiometric coefficient. For reaction, small a capital A plus small b capital B giving small c capital C plus small d capital D, Kc equals capital C raised to small c into capital D raised to small d divided by capital A raised to small a into capital B raised to small b. Equilibrium constant has constant value at a fixed temperature, and at this stage, all the macroscopic properties such as concentration, pressure, etc. become constant. For a gaseous reaction, equilibrium constant is expressed as Kp and is written by replacing concentration terms by partial pressures in Kc expression. The direction of reaction can be predicted by reaction quotient Qc, which is equal to Kc at equilibrium. Le Chatelier's principle states that the change in any factor such as temperature, pressure, concentration, etc. will cause the equilibrium to shift in such a direction so as to reduce or counteract the effect of the change. It can be used to study the effect of various factors such as temperature, concentration, pressure, catalyst, and inert gases on the direction of equilibrium, and to control the yield of products by controlling these factors. Catalyst does not affect the equilibrium composition of a reaction mixture, but increases the rate of chemical reaction by making available a new lower energy pathway for conversion of reactants to products and vice versa. All substances that conduct electricity in aqueous solutions are called electrolytes. Acids, bases and salts are electrolytes, and the conduction of electricity by their aqueous solutions is due to anions and cations produced by the dissociation or ionization of electrolytes in aqueous solution. The strong electrolytes are completely dissociated. In weak electrolytes, there is equilibrium between the ions and the unionized electrolyte molecules. According to Arrhenius, acids give hydrogen ions while bases produce hydroxyl ions in their aqueous solutions. Bronsted-Lowry, on the other hand, defined an acid as a proton donor and a base as a proton acceptor. When a Bronsted-Lowry acid reacts with a base, it produces its conjugate base and a conjugate acid corresponding to the base with which it reacts. Thus, a conjugate pair of acid-base differs only by one proton. Lewis further generalized the definition of an acid as an electron pair acceptor and a base as an electron pair donor. The expressions for ionization, equilibrium, constants of weak acids Ka and weak bases Kb are developed using Arrhenius' definition. The degree of ionization and its dependence on concentration and common ion are discussed. The pH scale, pH equals minus log H plus for the hydrogen ion concentration activity has been introduced and extended to other quantities. pOH equals minus log OH minus, pKa equals minus log Ka, pKb equals minus log Kb, and pKw equals minus log Kw, etc. The ionization of water has been considered, and we note that the equation pH plus pOH equals pKw is always satisfied. The salts of strong acid and weak base, weak acid and strong base, and weak acid and weak base undergo hydrolysis in aqueous solution. The definition of buffer solutions and their importance are discussed briefly. The solubility equilibrium of sparingly soluble salts is discussed, and the equilibrium constant is introduced as solubility product constant Ksp. Its relationship with solubility of the salt is established. The conditions of precipitation of the salt from their solutions and their dissolution in water are worked out. The role of common ion and the solubility of sparingly soluble salts is also discussed. Suggested activities for students regarding this unit. A. The student may use pH paper in determining the pH of fresh juices of various vegetables and fruits, soft drinks, body fluids, and also that of water samples available. B. The pH paper may also be used to determine the pH of different salt solutions, and from that he or she may determine if these are formed from strong or weak acids and bases. C. They may prepare some buffer solutions by mixing the solutions of sodium acetate and acetic acid and determine their pH using pH paper. D. They may be provided with different indicators to observe their colors in solutions of varying pH. E. They may perform some acid-base titrations using indicators. F. They may observe common ion effect on the solubility of sparingly soluble salts. G. If pH meter is available in their school, they may measure the pH with it and compare the results obtained with that of the pH paper. Exercises 6.1. A liquid is in equilibrium with its vapor in a sealed container at a fixed temperature. The volume of the container is suddenly increased. A. What is the initial effect of the change on vapor pressure? B. How do rates of evaporation and condensation change initially? C. What happens when equilibrium is restored finally, and what will be the final vapor pressure? 6.2. What is Kc for the following equilibrium when the equilibrium concentration of each substance is SO2 equals 0.60 m, O2 equals 0.82 m, and SO3 equals 1.90 m. 2 SO2 gas plus O2 gas gives 2 SO3 gas. 6.3. At a certain temperature and total pressure of 10 raised to 5 Pa, iodine vapor contains 40% by volume of I atoms. I2 gas gives 2I gas. Calculate Kp for the equilibrium. 6.4. Write the expression for the equilibrium constant Kc for each of the following reactions. 1. 2NOCl gas gives 2NO gas plus Cl2 gas. 2. 2CuNO3 solid gives 2CuO solid plus 4NO2 gas plus O2 gas. 3. CH3COO C2H5 aqueous plus H2O liquid gives CH3COOH aqueous plus C2H5OH aqueous. 4. Fe raised to 3 plus aqueous plus 3OH minus aqueous gives FeOH3 solid. 5. I2 solid plus 5F2 gives 2IF5. 6.5. Find out the value of Kc for each of the following equilibria from the value of Kp. 1. 2NOCl gas gives 2NO gas plus Cl2 gas. Kp equals 1.8 into 10 raised to minus 2 at 500 K. 2. CaCO3 solid gives CaO solid plus CO2 gas. Kp equals 167 at 1073 K. 6.6. For the following equilibrium, Kc equals 6.3 into 10 raised to 14 at 1000 K. NO gas plus O3 gas gives NO2 gas plus O2 gas. Both the forward and reverse reactions in the equilibrium are elementary bimolecular reactions. What is Kc for the reverse reaction? 6.7. Explain why pure liquids and solids can be ignored while writing the equilibrium constant expression. 6.8. Reaction between N2 and O2 minus takes place as follows. 2N2 gas plus O2 gas gives 2N2O gas. If a mixture of 0.482 moles N2 and 0.933 mole of O2 is placed in a 10-liter reaction vessel and allowed to form N2O at a temperature for which Kc equals 2 into 10 raised to minus 37, determine the composition of equilibrium mixture. 6.9. Nitric oxide reacts with Br2 and gives nitrosyl bromide as per reaction given below. 2NO gas plus Br2 gas gives 2NOBr gas. When 0.087 mole of NO and 0.0437 mole of Br2 are mixed in a closed container at constant temperature, 0.0518 mole of NOBr is obtained at equilibrium. Calculate equilibrium amount of NO and Br2. 6.10. At 450 K, Kp equals 2 into 10 raised to 10 per bar for the given reaction at equilibrium. 2 SO2 gas plus O2 gas gives 2 SO3 gas. What is Kc at this temperature? 6.11. A sample of HI gas is placed in flask at a pressure of 0.2 atm. At equilibrium, the partial pressure of HI gas is 0.04 atm. What is Kp for the given equilibrium? 2 HI gas gives H2 gas plus I2 gas. 6.12. A mixture of 1.57 mole of N2, 1.92 mole of H2 and 8.13 mole of NH3 is introduced into a 20-liter reaction vessel at 500 K. At this temperature, the equilibrium constant Kc for the reaction N2 gas plus 3H2 gas gives 2NH3 gas is 1.7 into 10 squared. Is the reaction mixture at equilibrium? If not, what is the direction of the net reaction? 6.13. The equilibrium constant expression for a gas reaction is Kc equals NH3 raised to 4, O2 raised to 5 divided by NO raised to 4, H2O raised to 6. Write the balanced chemical equation corresponding to this expression. 6.14. 1 mole of H2O and 1 mole of CO are taken in 10-liter vessel and heated to 725 K. At equilibrium, 40% of water by mass reacts with CO according to the equation. H2O gas plus CO gas gives H2 gas plus CO2 gas. Calculate the equilibrium constant for the reaction. 6.15. At 700 K, equilibrium constant for the reaction H2 gas plus I2 gas gives 2 HI gas is 54.8. If 0.5 moles per liter of HI gas is present at equilibrium at 700 K, what are the concentration of H2 gas and I2 gas, assuming that we initially started with HI gas and allowed it to reach equilibrium at 700 K? 6.16. What is the equilibrium concentration of each of the substances in the equilibrium when the initial concentration of ICl was 0.78 m? 2 ICl gas gives I2 gas plus Cl2 gas. Kc equals 0.14. 6.17. Kp equals 0.04 atm at 899 K for the equilibrium shown below. What is the equilibrium concentration of C2H6 when it is placed in a flask at 4 atm pressure and allowed to come to equilibrium? C2H6 gas gives C2H4 gas plus H2 gas. 6.18. Ethyl acetate is formed by the reaction between ethanol and acetic acid, and the equilibrium is represented as CH3COOH liquid plus C2H5OH liquid gives CH3COO C2H5 liquid plus H2O liquid. 1. Write the concentration ratio, reaction quotient QC for this reaction. Note, water is not in excess and is not a solvent in this reaction. 2. At 293 K, if one starts with 1 mole of acetic acid and 0.18 mole of ethanol, there is 0.171 mole of ethyl acetate in the final equilibrium mixture. Calculate the equilibrium constant. 3. Starting with 0.5 mole of ethanol and 1 mole of acetic acid and maintaining it at 293 K, 0.214 mole of ethyl acetate is found after some time. Has equilibrium been reached? 6.19. A sample of pure PCl5 was introduced into an evacuated vessel at 473 K. After equilibrium was attained, concentration of PCl5 was found to be 0.5 into 10 raised to minus 1 moles per liter. If value of Kc is 8.3 into 10 raised to minus 3, what are the concentrations of PCl3 and Cl2 at equilibrium? PCl5 gas gives PCl3 gas plus Cl2 gas. 6.20. One of the reactions that takes place in producing steel from iron ore is the reduction of iron 2 oxide by carbon monoxide to give iron metal and CO2. FeO solid plus CO gas gives Fe solid plus CO2 gas. Kp equals 0.265 atm at 1050 K. What are the equilibrium partial pressures of CO and CO2 at 1050 K if the initial partial pressures are PCO equals 1.4 atm and PCO2 equals 0.80 atm. 6.21. Equilibrium constant Kc for the reaction N2 gas plus 3H2 gas giving 2NH3 gas at 500 K is 0.061. At a particular time, the analysis shows that composition of the reaction mixture is 3 moles per liter N2, 2 moles per liter H2 and 0.5 moles per liter NH3. Is the reaction at equilibrium? If not, in which direction does the reaction tend to proceed to reach equilibrium? 6.22. Bromine monochloride BrCl decomposes into bromine and chlorine and reaches the equilibrium. 2 BrCl gas gives Br2 gas plus Cl2 gas, for which Kc equals 32 at 500 K. If initially pure BrCl is present at a concentration of 3.3 into 10 raised to minus 3 moles per liter, what is its molar concentration in the mixture at equilibrium? 6.23. At 1127 K and 1 atm pressure, a gaseous mixture of CO and CO2 in equilibrium with solid carbon has 90.55% CO by mass. C solid plus CO2 gas gives 2 CO gas. Calculate Kc for this reaction at the above temperature. 6.24. Calculate A. delta G minus and B. the equilibrium constant for the formation of NO2 from NO and O2 at 298 K. NO gas plus half O2 gas gives NO2 gas, where delta Fg minus NO2 equals 52 kilojoules per mole, delta Fg minus NO equals 87 kilojoules per mole, delta Fg minus O2 equals 0 kJ per mole. 6.25. Does the number of moles of reaction products increase, decrease, or remain same when each of the following equilibria is subjected to a decrease in pressure by increasing the volume? A. PCl5 gas gives PCl3 gas plus Cl2 gas. B. CaO solid plus CO2 gas gives CaCO3 solid. C. 3Fe solid plus 4H2O gas gives Fe3O4 solid plus 4H2 gas. 6.26. Which of the following reactions will get affected by increasing the pressure? Also mention whether change will cause the reaction to go into forward or backward direction. 1. COCl2 gas gives CO gas plus Cl2 gas. 2. CH4 gas plus 2S2 gas gives CS2 gas plus 2H2S gas. 3. CO2 gas plus C solid gives 2CO gas. 4. 2H2 gas plus CO gas gives CH3OH gas. 5. CaCO3 solid gives CaO solid plus CO2 gas. 6. 4NH3 gas plus 5O2 gas gives 4NO gas plus 6H2O gas. 6.27. The equilibrium constant for the following reaction is 1.6 into 10 raised to 5 at 1024 K. H2 gas plus Br2 gas gives 2 HBr gas. Find the equilibrium pressure of all gases if 10 bar of HBr is introduced into a sealed container at 1024 K. 6.28. Dihydrogen gas is obtained from natural gas by partial oxidation with steam as per following endothermic reaction. CH4 gas plus H2O gas gives CO gas plus 3H2 gas. A. Write as expression for Kp for the above reaction. B. How will the values of Kp and composition of equilibrium mixture be affected by 1. Increasing the pressure, 2. Increasing the temperature, 3. Using a catalyst. 6.29. Describe the effect of A. Addition of H2, B. Addition of CH3OH, C. Removal of CO, D. Removal of CH3OH on the equilibrium of the reaction. 2H2 gas plus CO gas gives CH3OH gas. 6.30. At 473 K, equilibrium constant Kc for decomposition of phosphorus pentachloride PCl5 is 8.3 into 10 raised to minus 3. If decomposition is depicted as PCl5 gas gives PCl3 gas plus Cl2 gas, delta RH minus equals 124 kilojoules per mole. A. Write an expression for Kc for the reaction. B. What is the value of Kc for the reverse reaction at the same temperature? C. What would be the effect on Kc if 1. More PCl5 is added, 2. Pressure is increased, 3. The temperature is increased. 6.31. Dihydrogen gas used in Haber's process is produced by reacting methane from natural gas with high temperature steam. The first stage of two-stage reaction involves the formation of CO and H2. In second stage, CO formed in first stage is reacted with more steam in water-gas shift reaction. CO gas plus H2O gas gives CO2 gas plus H2 gas. If a reaction vessel at 400 degrees Celsius is charged with an equimolar mixture of CO and steam such that PCO equals PH2O equals 4 bar, what will be the partial pressure of H2 at equilibrium? Kp equals 10.1 at 400 degrees Celsius. 6.32. Predict which of the following reaction will have appreciable concentration of reactants and products. A. C12 gas gives 2Cl gas, Kc equals 5 into 10 raised to minus 39. B. C12 gas plus 2NO gas gives 2NOCl gas, Kc equals 3.7 into 108. C. C12 gas plus 2NO2 gas gives 2NO2Cl gas, Kc equals 1.8. 6.33. The value of Kc for the reaction 3O2 gas gives 2O3 gas is 2 into 10 raised to minus 50 at 25 degrees Celsius. If the equilibrium concentration of O2 in air at 25 degrees Celsius is 1.6 into 10 raised to minus 2, what is the concentration of O3? 6.34. The reaction CO gas plus 3H2 gas gives CH4 gas plus H2O gas is at equilibrium at 1300 K in a 1 liter flask. It also contains 0.30 moles of CO, 0.10 mole of H2 and 0.02 mole of H2O and an unknown amount of CH4 in the flask. Determine the concentration of CH4 in the mixture. The equilibrium constant Kc for the reaction at the given temperature is 3.90. 6.35. What is meant by the conjugate acid-base pair? Find the conjugate acid-base for the following species: HNO2, Cn-, HClO4, F-, OH-, CO3 raised to 2- and S raised to 2-. 6.36. Which of the following are Lewis acids? H2O, BF3, H+, and NH4+. 6.37. What will be the conjugate bases for the Bronsted acids? HF, H2SO4, and HCO3-. 6.38. Write the conjugate acids for the following Bronsted bases: NH2-, NH3, and HCOO-. 6.39. The species H2O, HCO3-, HSO4-, and NH3 can act both as Bronsted acids and bases. For each case, give the corresponding conjugate acid and base. 6.40. Classify the following species into Lewis acids and Lewis bases and show how these act as Lewis acid or base: A, OH-, B, F-, C, H+, D, BCl3. 6.41. The concentration of hydrogen ion in a sample of soft drink is 3.8 into 10 raised to minus 3 m. What is its pH? 6.42. The pH of a sample of vinegar is 3.76. Calculate the concentration of hydrogen ion in it. 6.43. The ionization constant of HF, HCOOH, and HCN at 298 K are 6.8 into 10 raised to minus 4, 1.8 into 10 raised to minus 4, and 4.8 into 10 raised to minus 9 respectively. Calculate the ionization constants of the corresponding conjugate base. 6.44. The ionization constant of phenol is 1 into 10 raised to minus 10. What is the concentration of phenolate ion in 0.05 m solution of phenol? What will be its degree of ionization if the solution is also 0.01 m in sodium phenolate? 6.45. The first ionization constant of H2S is 9.1 into 10 raised to minus 8. Calculate the concentration of HS minus ion in its 0.1 m solution. How will this concentration be affected if the solution is 0.1 m in HCl also? If the second dissociation constant of H2S is 1.2 into 10 raised to minus 13, calculate the concentration of S raised to 2 minus under both conditions. 6.46. The ionization constant of acetic acid is 1.74 into 10 raised to minus 5. Calculate the degree of dissociation of acetic acid in its 0.05 m solution. Calculate the concentration of acetate ion in the solution and its pH. 6.47. It has been found that the pH of a 0.01 solution of an organic acid is 4.15. Calculate the concentration of the anion, the ionization constant of the acid, and its pKa. 6.48. Assuming complete dissociation, calculate the pH of the following solutions: A, 0.003 m HCl, B, 0.005 m NaOH, C, 0.002 m HBr, D, 0.002 m KOH. 6.49. Calculate the pH of the following solutions: A, 2 grams of TLOH dissolved in water to give 2 liters of solution. B, 0.3 grams of CaOH2 dissolved in water to give 500 ml of solution. C. 0.3 grams of NaOH dissolved in water to give 200 ml of solution. D. 1 ml of 13.6 m HCl is diluted with water to give 1 liter of solution. 6.50. The degree of ionization of a 0.1 m bromoacetic acid solution is 0.132. Calculate the pH of the solution and the pKa of bromoacetic acid. 6.51. The pH of 0.005 m codeine C18H21NO3 solution is 9.95. Calculate its ionization constant and pKb. 6.52. What is the pH of 0.001 m aniline solution? The ionization constant of aniline can be taken from table 6.7. Calculate the degree of ionization of aniline in the solution. Also calculate the ionization constant of the conjugate acid of aniline. 6.53. Calculate the degree of ionization of 0.05 m acetic acid if its pKa value is 4.74. How is the degree of dissociation affected when its solution also contains A. 0.01 m, B. 0.1 m in HCl. 6.54. The ionization constant of dimethylamine is 5.4 into 10 raised to minus 4. Calculate its degree of ionization in its 0.02 m solution. What percentage of dimethylamine is ionized if the solution is also 0.1 m in NaOH? 6.55. Calculate the hydrogen ion concentration in the following biological fluids whose pH are given below. A. Human muscle fluid 6.83. B. Human stomach fluid 1.2. C. Human blood 7.38. D. Human saliva 6.4. 6.56. The pH of milk, black coffee, tomato juice, lemon juice and egg white are 6.8, 5, 4.2, 2.2 and 7.8 respectively. Calculate corresponding hydrogen ion concentration in each. 6.57. If 0.561 grams of KOH is dissolved in water to give 200 ml of solution at 298 K, calculate the concentrations of potassium, hydrogen and hydroxyl ions. What is its pH? 6.58. The solubility of SrOH2 at 298 K is 19.23 grams per liter of solution. Calculate the concentrations of strontium and hydroxyl ions and the pH of the solution. 6.59. The ionization constant of propanoic acid is 1.32 into 10 raised to minus 5. Calculate the degree of ionization of the acid in its 0.05 m solution and also its pH. What will be its degree of ionization if the solution is 0.01 m in HCl also? 6.60. The pH of 0.1 m solution of cyanic acid HCNO is 2.34. Calculate the ionization constant of the acid and its degree of ionization in the solution. 6.61. The ionization constant of nitrous acid is 4.5 into 10 raised to minus 4. Calculate the pH of 0.04 m sodium nitrite solution and also its degree of hydrolysis. 6.62. A 0.02 m solution of pyridinium hydrochloride has pH equals 3.44. Calculate the ionization constant of pyridine. 6.63. Predict if the solutions of the following salts are neutral, acidic or basic: NaCl, KBr, NaCN, NH4NO3, NaNO2 and Kf. 6.64. The ionization constant of chloroacetic acid is 1.35 into 10 raised to minus 3. What will be the pH of 0.1 m acid and its 0.1 m sodium salt solution? 6.65. Ionic product of water at 310 K is 2.7 into 10 raised to minus 14. What is the pH of neutral water at this temperature? 6.66. Calculate the pH of the resultant mixtures. A. 10 ml of 0.2 m CaOH2 plus 25 ml of 0.1 m HCl. B. 10 ml of 0.01 m H2SO4 plus 10 ml of 0.01 m CaOH2. C. 10 ml of 0.1 m H2SO4 plus 10 ml of 0.1 m KOH. 6.67. Determine the solubilities of silver chromate, barium chromate, ferric hydroxide, lead chloride and mercurous iodide at 298 K from their solubility product constants given in table 6.9. Determine also the molarities of individual ions. 6.68. The solubility product constant of Ag2CrO4 and AgBr are 1.1 into 10 raised to minus 12 and 5 into 10 raised to minus 13 respectively. Calculate the ratio of the molarities of their saturated solutions. 6.69. Equal volumes of 0.002 m solutions of sodium iodate and cupric chlorate are mixed together. Will it lead to precipitation of copper iodate? For cupric iodate, Ksp equals 7.4 into 10 raised to minus 8. 6.70. The ionization constant of benzoic acid is 6.46 into 10 raised to minus 5 and Ksp for silver benzoate is 2.5 into 10 raised to minus 13. How many times is silver benzoate more soluble in a buffer of pH 3.19 compared to its solubility in pure water? 6.71. What is the maximum concentration of equimolar solutions of ferrous sulfate and sodium sulfide so that when mixed in equal volumes there is no precipitation of iron sulfide? For iron sulfide, Ksp equals 6.3 into 10 raised to minus 18. 6.72. What is the minimum volume of water required to dissolve 1 gram of calcium sulfate at 298 K? For calcium sulfate, Ksp is 9.1 into 10 raised to minus 6. 6.73. The concentration of sulfide ion in 0.1 m HCl solution saturated with hydrogen sulfide is 1 into 10 raised to minus 19 m. If 10 ml of this is added to 5 ml of 0.04 m solution of the following: FeSO4, MnCl2, ZnCl2 and CdCl2, in which of these solutions precipitation will take place?